Okay, can everyone hear me okay? Yeah, great.
Yes.
Yeah, like I said, we'll want to be able to generate this. So what I meant by drawing the lines, the first line here, this is our 100 or 1s orbital. And we're going to mimic this here. And so 200. Now there's a big jump in energy here, but there's not a big jump in going from the 2s to the 2p. And so the 2p, we have three of them. These are equivalent in energy. These are our 2p's. What are they? They're the 2-1 minus 1, the 2-1-0, and the 2-1-1. Yeah, that's correct, Kazra. The next exam is going to be, the exam tomorrow is going to be take home. It's going to be similar to what we saw. And so we were talking, there are a total of 4 orbitals, and the n equals 2, and the n equals 3. There are a total of 9 orbitals distributed amongst 3 sublevels: the 3s sublevel, the 3p sublevel here, which would be 3-1 minus 1, 3-1-0, 3-1-1, and then the 3D. Now, what's happening with the energies is going to be, if you look at this, this is the pattern that we see for the energies. And so this is off bow. This is off bow here. That's off bow. And so off bow just says, for the lowest, this is an off bow principle. I think I might have written this earlier. I'm not sure. The off bow principle just states that we should fill the lowest energies first, and then the higher energies. The lowest energy is the 1s, and then followed by the 2s, and then the 2p, the 3s, and then the 3p, the 4s. But something funny happens here with the 3D. The 3D should be next, but the 4S sinks in there. In fact, the 3D get pushed up here in energy, and they're 5 3D orbitals. And so these are the 3D. What are they? They're the 3-2 minus 2, the 3-2 minus 1, the 3-2-0, the 3-2-1, and the 3-2-2. Those are the 5D orbitals. Each one has a unique set of 3 quantum numbers. But what happens here is the 4s sneaks in there. And so these are the energies, how we're going to order the energies, as far as. And so the 4s is actually lower in energy than the 3D. We see it here. The 4s is actually lower in energy than the 3D. And so we should be able to draw that here. And then what comes next? The 4p. And so the 4p come here. That would be the 4p. Now, after the 4s, the 4p, we expect 4d. But if you look at the 4d are way up here above the 5s. So there's a gap here up to the 5s, which is 500. And then we have the 5p like this. But the 5p are actually higher in energy than the 4d. So the 4d kind of split the energy here between the 5s and the 5p. So it goes 5s, 4d, 5p. So we could see that here in this chart. It goes 5s, 4d, 5p. And so this would be the 4d. And so things start to get a little bit mixed up. And so what we do is we don't order things based on n. We order things based on closely spaced orbitals in terms of energy. These are closely spaced orbitals in terms of energy. And so, so what we're going to do here is this. We're going to divide it into shells of orbitals. And the shells of orbitals are going to be based on here, on closely spaced. Oops, green's not a good color to contrast that. Let's go with white. And so here we call this the first shell. The first shell only has 1 orbital. And then we go to the second shell. The second shell has 4 orbitals. That's the n equals 2. So n equals 2 energy level and n equals 2 shell are the same thing. But when we go to n equals 3, the 3D are left out of there. And so let's try to, yeah. the 3D actually get placed in the next shell. Oh, come on. And so the next shell here consists of these orbitals, the 4s, the 3d, and the 4p. That's in the fourth shell. The fifth shell, consists of these. The sixth shell is going to consist of these orbitals here. And so let's break it up into shells here. Let's go with red. So we got, okay, that's not working. The fifth shell is going to consist of the 5s, the 5p, and the 4d. Once we get to the sixth shell, we throw in the 4f's in there as well. So the sixth shell is going to have the 6s, and then it's going to go to 4f. So it goes 6s here to the 4f, 6s to the 4f, 6s to the 4f, to the 5d. So 6s, 4f, 5d. To the 6p. And so the sixth shell would have those orbitals here. That would be the sixth shell. Now, the next thing is how many electrons does each shell hold? Well, it depends. How many orbitals does each shell, how many, how many electrons does each orbital have? Oh, by the way, this energy level diagram doesn't look anything like the one in your book. This one that you see in your book here is garbage. And so don't even bother with that one here. And so let's take a look here. All right, who are these other people? This person is Pauli. And he's famous for the Pauli exclusion principle. But Pauli exclusion principle, did I already talk about this? I'm not sure. The deja vu moment. But the Pauli exclusion principle says no two electrons in an atom can have the same set of 4 quantum numbers. And so what that means is it means that if I put in one electron here, now the electrons are going to have something called spin. And so the last quantum number, the 4th quantum number, is spin. The first 3 quantum numbers define the orbital. The 4th quantum number tells us if it's spin up, is for the electron. Quantum number is for the electron. It could be spin up, which is plus 1/2, or spin down. These are the only 2 states. Spin down is minus 1/2. And so we could represent the electron with an arrow like this, showing spin up plus 1/2 or spin down minus 1/2. And so if we put one electron in this 1s orbital, spin up, then that electron would be a 1, 0, 0, 1/2 electron. It's 1, 0, 0 because it's a 1, 0, 0 orbital, and spin up 1/2. That means the next electron in there cannot be spin up. If I put a spin up electron here, then I have 2 electrons in the same atom with the same set of 4 quantum numbers. That's a violation of the Pauli exclusion principle. So the second electron here has to be spin down. So it's going to be a 1, 0, 0, which tells me what orbital it's in, and minus 1/2 tells me it's spin down. And so those are the electrons here. Now, this next person is Hund, and he's famous for Hund's rule. Hund's rule just states that fill same energy orbitals, we call same energy energetically degenerate. Energetically degenerate means they're the same energy. Fill energetically degenerate singly with parallel spin. All right, so what that means is off-bow says fill the orbitals from lowest energy to highest energy to get the lowest energy state. So if I have 3 electrons, the third electron has to jump up to the next higher energy orbital. It would go here. This would be like lithium. Lithium has 3 electrons. Beryllium has 4 electrons, so the 4th electron would go spin down. So this would be a 200 plus 1/2. This would be a 200 minus 1/2. Now the next electron has to jump up to the next energy. So it could pick any of these 3. All 3 are energetically degenerate. And so that what that means is it doesn't matter. They're all the same energy. The only difference is one's on the X, the other's on the Y, the other's on the Z. So you can pick any of the 3, and it could be spin up or spin down. It doesn't matter. But once you pick one, then it makes a difference how we fill the next one. How we fill the next one is we don't want to pair it. This is called pairing if I put 2 electrons in an orbital, because electrons are negatively charged, so they like to spread out. And so it's going to, Hund's rule says it's going to fill the next orbital rather than pair. And so fill singly. And so this would be beryllium would be 3, carbon would have 4 electrons like this, and then nitrogen would have 5 electrons, I mean, in this shell. A total of 7 electrons altogether. Okay, once I fill these singly, then oxygen has to pair because there's no more singles. And so finally I'm going to have to pair it. Well, pairing, you know, the electrons would rather spread out, but there's no choice here. It's got to pair. So this would be like oxygen, the total of 2, 4, 6, 8 electrons altogether. And then in this shell, it has 6 electrons. In this shell, it has 2 electrons here. And so that would be it here. Okay, so that's the off-bow principle is just, you know, going from lowest to highest energy. All right, we're gonna continue on here. Hold on just a second. I'll be right back. All right, so we got to get good at drawing energy level diagrams. So let's see if we can do it without the guide there. And so the first one is the 1s or the 100, and then I want to do a gap here. This would be the 2s or the 200, and then a small gap here to the next subshell. Should be the 2p, which we'll have the 2,1 minus 1, 2,10, and the 2,11 orbitals. And then a larger gap to the 3s, but not as big as this. The biggest gap will be the 1s to the 2s. So this will be a 3s, to a 3p. 3s is a 300. 3p is a 3-1 minus 1, 3-1-0, and a 3-1-1. And then we're going to look at the shells here. The shells are going to be closely spaced orbitals. And so again, what happens here with the D, we'll talk about. So this is going to be the first shell. In the first shell, there's only one subshell. In the second shell, there are two subshells. So this is the second shell. And the two subshells are the S and the P. In the first shell, you know, the first shell can hold 2 electrons max. In the second shell, we have 4 orbitals. 4 orbitals can hold 8 electrons max. 2 electrons max. In the third shell, the 3D aren't in the third shell. As you recall, the 3D get pushed up into the fourth shell. And so in the third shell, it's tricky because in the third shell, in n equals 3, we expect 9 orbitals. But in this case, in the third shell, we're only going to have 2 subshells. The 3s subshell and the p subshell. That's 4. This is going to be 8 electrons max here. Now, when we get to the fourth subshell, and we want to be able to write this up to the fourth subshell. The second shell has 8 electrons max. It doesn't have to have 8 electrons, but it could have up to a maximum of 8 electrons, meaning, let me see, can I delete that? Come on. Let's get rid of that here. Okay, meaning I can put 2 electrons in the S and then a total of 6 electrons, 2, 4, 6 total in the P. So altogether 8 in the second shell. Third shell is the same thing, 8 electrons max. Now the fourth shell is a little different. So let's go ahead and draw out the fourth shell. You should be able to draw this out without looking. You know, you need to have this memorized up through the fourth shell. And so without looking, I'm going to have the 4s. About, you know, I can also use the off-bow pyramid, you know, if I wanted to, 1s, 2s, you know, I could use that off-bow pyramid to figure this out. 2p, like this. 3s, going arrows like this. So 3s, 3p, 3d, 4s, 4p, 4d, 4f. And so I could use this to figure it out. But anyway, it's going to go 4s. Uh-oh. Are you guys still there? Yeah, it looks like it. All right. It's going to go 4s to the 3d. And so the 3D, since this is a different subshell, I'm going to write it over here to the right. So I have all the P's lined up. I have all the S's lined up. Now I'm going to have the D's lined up over here, the 3D. Now the 3D is going to be 3, 2, negative 2, 3, 2, negative 1, 3, 2, 0, 3, 2, 1, 3, 2, 2. And then I'm going to have the 4P just above the 3D. And so it's going to go 4s to 3d to 4p in terms of energy. So 4s to 3d to 4p. You can see it here in terms of energy, 4p. Now the 5s is going to be in the next shell. So 5s goes. And so what we want to do is we want to draw this to the fourth shell. In other words, memorize this to the fourth shell. Now, how many electrons can the fourth shell hold altogether max? So this would be the fourth shell. How many electrons can we put in there maximum? 18, that's correct. 18 electrons is the max in the fourth shell. Good. That's good. So let's go ahead and fill these with electrons. Now the orbitals are gonna, let's kind of draw or sketch the orbitals out. a little bit. You know, a 1s orbital is going to be kind of a small spherical orbital. And so we could draw like a sphere and say 90% of the dots are inside, you know, 95% of the dots are inside, 5% are outside. The 2s are going to be bigger, right? The 3s are going to be bigger. The 4s are going to be bigger, much bigger in terms of energy. And the p's are going to have this kind of shape, you know, like a figure-8 shape. We'll throw the nucleus in the center. And so we got a P like this, and then we got a P like this, and then we got a P that kind of sticks out like this. Now that's a 2P. The 2P and the 2S are kind of the same kind of size, roughly. And the 3Ps are going to be a lot bigger, you know. A lot bigger. There are other structural features to this, which you can get into in Chem 1A. Not really going to get into it. Now the 3Ds are kind of small compared to the 4s. You know, the 3Ds are kind of on par size-wise with the 3S and the 3Ps. They're like 4-leaf clovers. And so this would be one. They're like, most of them, 4 out of the 5 are like 4-leaf clovers, and then they're just positioned differently. So these, whereas the 4S are kind of a lot bigger, you know, so the 4Ps are a lot bigger, you know, and so the 3Ds are kind of small compared to the 4S and the 4P, but energetically they're kind of similar in terms of energy. So this is why, even though the 3s are kind of small in the much larger 4s, they're in the same shell because the 3Ds energetically are higher in energy than the other 3, the 3S and the 3Ps. Does that make sense? And so the 3Ds are kind of small compared to, but they're in the same shell, so it's all right. All right, now let's throw some electrons in there. And so a hydrogen has a, you know, when I look at the H atom here, let's see what color I do. All right, when I look at the hydrogen atom, I have a proton in the nucleus, and then I have an electron. This electron is going to be in the 1s orbital. I'll just draw it big here. This is a 1s orbital. There are different ways of representing this. Okay, one way is I could have a shell like this. This is what we call the 95% boundary. And so 95% probability this electron is going to be within this shell boundary. This is not a wall. You know, the electron can easily go outside, but, you know, it becomes less and less probable that it goes outside. It's like the bird. You know, if you have a low energy bird, you know, the farther away from the nest, the less probable. And so there's only 5% chance it's outside this boundary, but it can be anywhere outside this boundary. The farther you get away, the lower the probability becomes. I mean, there's even a probability that this is infinitely far away, but that's, you know, the probability is very exceedingly small, but there's still non-zero probability. The probability goes to 0 at infinity, you know, if that's there. And so this is 1s orbital. That's one way of representing it. Another way of representing hydrogen electron is via like a cloud, like an electron cloud. And so alternatively, we can show this kind of probability rather than as a 95% boundary, we can show it as dots. And so most likely that bird is going to be, or the electron is going to be close to the nucleus. It's not going to go too far from the nucleus. And then as we get farther and further away from the nucleus, we're going to have fewer and fewer dots, you know, as we get farther away. And so what this 95% boundary is doing is it's capturing 95% of the dots here, and 5% of the dots lie outside this. And that, you know, for higher energy, yeah, higher energy, like for example, 4s orbital, you know, there's still a chance that that electron's very close to the nest, but there's a much higher probability than a 1s orbital that it could be out here, you know, So this is another way of visualizing this. And so we got a much bigger orbital here. Because if you got a lot more energy, then it can be a lot farther away from the nucleus. Yeah. All right. So so if we're looking at a hydrogen atom, then we have an electron in there. Now, electron is going to have either spin up or spin down. So this electron can either be spin up, you know, the arrow pointed up, or it could be spin down, the arrow pointed down. It doesn't matter which one. It makes a difference when you throw hydrogen into a magnet. Then it makes a difference. And then we can see the difference, you know, if it's spin up or spin down. If you throw hydrogen atoms into a giant magnet. Well, we aren't going to do it. All right, now what if we have helium? If we have helium, then what's going to happen is we're going to just throw another electron in there. Now, something happens with helium. Helium turns out to be a lot smaller, but you think it would be bigger. You would think it would be bigger because it's got more stuff, but it's actually smaller. And so let's just briefly look at the reason why helium would be smaller. Try to find a different color here. And so if I go to helium here, let's draw it over here. It's a smaller atom. The reason it's smaller is because it has 2 protons in the nucleus and 2 neutrons. And so it's got 2 protons. Well, if you have 2 protons, then you got twice the electrical attraction, you know, twice the electrical attraction. So if you're an electron out here, you're going to be pulled in closer to helium. As if you have 2 protons here, it's like, you know, those tractor beams in science fiction. What it's going to do is it's going to pull in the electrons, whereas here it's a lot less, forceful, or a lot less strong. And so what that's going to do is it's going to contract the 95%. This is like a this is like a, you know, let's say let's say you're a child playing and your mother's very strict. They're going to keep a tight leash on you, versus this one would be a lot more relaxed, you know. So this electron can travel further away here. But when you got 2 protons in there, it pulls it in. And so the 1s orbital, not only is it small, but its size depends on how many protons we have in there. You know, the more protons we have in the nucleus, the smaller the 1s orbital is. So 1s orbital on hydrogen is a lot bigger than a 1s orbital on helium. When we go to lithium with 3 protons, the 1s orbital is a lot smaller in lithium. However, lithium is not a smaller atom. Lithium turns out to be a bigger atom. The reason why lithium is a bigger atom is because we got another orbital here. We got another shell. So when we jump to lithium, for example, here, let's do that. Here. When we jump to lithium, the 1s orbital is tiny because we have 3 protons in that nucleus, plus neutrons. I'm not going to draw the neutrons out, but those 3 protons are really going to pull in the 1s orbital electrons. And so the 1s orbital is small. It'll be the smallest of these 3. But the situation with lithium is it's got a big 2s orbital there. And so we got the 1s orbital here, but we also have the 2s orbital here. The 2s orbital is a lot bigger, like 4 times bigger. And there's an electron in the 2s orbital here, like that. And so when we go to helium, we have to throw 2 electrons in the 1s orbital. 1 electron has to be spin up. The other electron has to be spin down. So we got those 2 electrons. When we go to lithium, then we're going to have the 2 electrons in the 1s, 1 spin up, 1 spin down, like this. But now we have a 2s electron. The 2s electron can be it could either be spin up or spin down. We'll just throw it spin up like this here. And so lithium is a bigger atom here, even though it has more protons because it has another shell. Now these shells, each successive shell, the atoms are going to get bigger and bigger and bigger. You know, the orbitals are bigger. And so this is going to make an impact on that. Now, to draw this takes up a lot of space. And so we have electron configurations. Electron configurations aren't as good as energy level diagrams. Energy level diagrams give us a lot more information. But if you don't have much space, then we'll do an electron configuration. So for example, hydrogen, we call it a 1s1. That is, we have one electron in the 1s orbital. For helium, we call it a 1s2. For lithium, we call it a 1s2, 2 electrons in the 1s, and then 2s1, 1 electron in the 2s. And so this is kind of the shorthand way, but it doesn't show us as much information. Let's keep going. And so beryllium is going to fill up that. And so beryllium, we'll have that. Beryllium is actually going to be bigger or smaller than lithium. What do you think? Should beryllium, well, beryllium, should it be bigger or smaller than lithium? Okay, beryllium has 4 protons. It has 4 protons, so the 1s is going to be very small, for sure. 1s is going to be very small. But what about the 2s? It turns out the 2s is also going to be smaller. Because both are going, because the situation here is this. You might think the 2s is bigger because it's got 2 electrons, but the electrons kind of want to stay away from each other. And so when this electron is going to see the greater nuclear charge here. This electron, it sees, you know, the +3 kind of thing, except some of that +3 is blocked by the 1s electrons. Well, this electron is going to be seeing the +4 of the nucleus, but some of that +4 is going to be blocked by the 1s. But, you know, it's kind of the same scenario. If some of that charge is blocked by the 1s, then we're going to get the same kind of blocking, the same kind of shielding. We call this shielding. And so what turns out that is the 2s is actually smaller still, because this electron sees more positive charge. This electron sees more positive charge. Even though we have 2 of them, it's going to be like that science fiction tractor beam, you know, where it pulls in the electrons closer to the nucleus, you know, like in Star Wars or whatever. And so it's going to shrink down the atom. So when we go to beryllium, beryllium actually turns out to be smaller than lithium. Right? But lithium turns out to be bigger than helium. And lithium is going to be bigger than helium because we're going up in a shell. We're adding a shell. But once we're in the same shell, as we go across here, the atoms become smaller. The atoms become smaller as we go across because we're increasing the number of protons, but we aren't adding another shell. Atoms get bigger as we go up because each time we go up a level, we're adding another shell. And so it's a smaller 1s and a smaller 2s, causing beryllium to be smaller. After we go to beryllium, we go to boron. Boron is even smaller than beryllium. And then Hund's rule says carbon goes like this. And so let's stop at carbon. You know, the electron configuration for carbon would be 1s2, 2s2, 2p2. Now, the electron configuration doesn't tell us. It doesn't show us if these are paired or unpaired. And so this is not as descriptive as an orbital box diagram. And so some people do an orbital box diagram, show 1s2 like that, and then 2s2 with boxes. And then we're going to have 3 boxes for the 2p. So the top line is electron configuration here. The bottom line is what we call an orbital box diagram. This is orbital box diagram. Orbital box diagram is better. The best is an energy level diagram, but it takes up a lot of space. The most compact is an electron configuration, and a compromise is an orbital box diagram. Orbital box diagram, you can see that these 2 electrons are not paired. These 2 electrons are individual in separate orbitals for carbon. It's orbital box. So we go carbon to nitrogen. Nitrogen is 1 more electron. Now, an interesting thing happens. When you're an oxidizer or when you're a reducer, like nitrogen's an oxidizer, but it can be oxidized, you know. as we saw. Like carbon can be oxidized as well. So, so what happens is if you're an oxidizer reducer, you're dealing with these electrons, the outermost electrons. So if something comes in to attack, let's say I'm going to oxidize lithium. I'm going to attack lithium. If I attack lithium, I'm going to attack the outermost electron. The outermost electron is the electron furthest away from the nucleus. So this would be the electron furthest away from the nucleus, this one here. So if I'm an oxidizing agent, I'm going to come and pluck that one off. And so we have a name for the outermost electrons. The name for the outermost electrons would be valence electrons. The valence electrons are going to be the outermost, in other words, the outermost are going to have the highest N value. You remember, the bigger the N, the bigger the orbital. So N equals 1, N equals 2, N equals 3, N equals 4. So the highest N, outermost, and so in this case, the highest N is 2. And so nitrogen actually has 1, 2, 3, 4, 5 total electrons in the outermost shell. Now this is the inner shell. These aren't touched because, you know, if you're an oxidizer, you have to get through the outer ones first before you get to the inner. And once you get through the outer ones, it becomes very difficult to do these. These are the core electrons. Core electrons are inner shell electrons. Inner shell electrons. Now chemistry happens with the valence electrons. You know, either we're going to fill up this shell. So nitrogen can gain 3 electrons to fill up this shell, or it could lose 5 electrons to completely get rid of this shell. Its preference is to gain 3 rather than losing 5, but it can lose 5. It's possible. But it's got to be stabilized in a sense. And so the chemistry happens with the outermost shell. So this is why, you know, when we're looking at range of charges like carbon, you know, carbon ranges from, you know, +4 if it loses all 4, or -4 if it gains 4 to fill up this shell. And so chemistry happens here with the valence electrons. All right, we're going to continue filling these up with electrons. And so that would be nitrogen. Oxygen, we'd have to pair this. You know, Hund's rule says just fill these singly. And so oxygen's 2 electrons short of filling. Fluorine is only 1 electron short, and then neon has it filled. So neon has a filled shell. It has a filled valence shell and a filled core. And so that's what we call noble gas. Helium has a filled shell. The first shell's filled. Neon would have the second shell filled. And so if we fill this up to max here, then we get the neon configuration. If we fill this to the max here, we get the helium. These square brackets mean electron configuration here. If we fill this shell, the next shell up, we get argon here. And so going here from neon, we'll go to sodium, to magnesium, to aluminum, you know, to what comes after aluminum, silicon. After silicon comes phosphorus, and then sulfur, and then chlorine, and then argon. That fills that shell up. And then we go over here, sodium, magnesium, this would be potassium, right? Sodium, magnesium, sodium, lithium, sodium, potassium, yeah. Potassium, and then under magnesium is calcium. And then here, we're going to jump to the D. This would be scandium. Scandium to chromium, not chromium, scandium to titanium, etc. Now, when we get to this point, it gets mixed up. What's valence and what core? It turns out that because this shell's kind of screwed up, this shell, because we got three n equals 3 orbitals are a lot smaller. And so these are often considered inner shell. Inner shell here. Because n equals 3 is smaller than n equals 4. N equals 4, this would be outer shell. But even though this is inner shell, sometimes these can react. For example, titanium, this would be titanium. Titanium can lose 2 electrons here, but which 2 would it lose first? Well, if you're an oxidizer, it turns out it loses the 4s first because the 3d are closer in. So it has to eat through the 4s electrons first, the oxidizer has to, before it hits the 3d. And so any +2 is a common charge here. For this. We're going to get into it more, and +4 if we lose these. So sometimes inner shell electrons, especially partially filled D, can react as well. But for the most part, it's just outer shell electrons that play a role in the chemistry. So let's take a look at some more examples of this now. Here. Well, for one thing, the periodic table is arranged in terms of shell. And so the first row here is the first shell. The first shell can hold a max of 2 electrons, hydrogen and helium. Okay, this is going to be the second shell, which can hold 8 electrons total. This is why there are 8 elements in the second shell. Each element adds 1 more electron. And so the second shell begins with sodium to magnesium, to, lithium, sorry. Lithium to beryllium, to boron, to carbon, nitrogen, oxygen, fluorine, neon. And so there are 8 elements. Each element corresponds to adding 1 additional electron. The third shell, the same thing. 8 elements from, in this case, it would not, it'd be from sodium to argon. Argon here. This would be the third shell. Now the fourth shell is going to have the 4s, the 3d, and the 4p in that order. 4s, 3d, 4p. That would be the fourth shell here. Fifth shell is the 5s to the 4d to the 5p. This is the fifth shell. Now the sixth shell is funny because we go 6s and then drop down here to the 4f. So it goes 6s, 4f, 5d, 6p. Okay. The sixth shell can hold a lot more electrons. The fifth shell only holds 18 electrons. The sixth shell would hold 18 plus another 14 electrons. So 32 electrons in the sixth shell. The sixth shell can hold up to 32 electrons max. Because we're adding 14 from the 5f. There's 7 orbitals here. Each orbital can hold 2. So 1, 2, 3, 4, 5, 6, 7 orbitals here. Each orbital holds 2, so that's 14 electrons there. So we have the electron configuration shown here for all the elements here. The electron configurations are using these, what we call core abbreviations. And so do you see neon in square brackets here? Neon means, all the way to neon, which is 1s2, 2s2, 2p6, and then on top of that we have 3s1. And so this is just an abbreviation for all these here. And then on the next, in the fourth shell here, we're using the argon core abbreviation. So argon core abbreviation would be 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s1 for those. And then we go across here. Now, core versus valence electrons, it's easy to see here. I mean, we could have done the same thing with helium core. I don't know why they didn't do it here. And so this is going to be helium core. 1s2 is the helium core. It's helium core. And so the valence are just 2s2, 2p1. So there's 3 valence electrons here. Over here, the core is 1s2. So the valence is 2s1. So we have 1 valence electron. Here we're going to have 2 valence electrons, 3 valence electrons, 4 valence electrons. So carbon has 4 valence electrons because this is the core, and therefore these are the valence here, 2s2, 2p6, 2p2, which is a total of 4. Now silicon has 4 valence electrons as well because now it's got neon core filled, and then the outermost shell is going to be 3s2, 3p2. That's 4 valence electrons. Germanium looks, how many valence electrons does germanium have? And so if we look at the argon core, it appears to have 2 plus 10 is 12 plus 2 is 14. It appears to have 14 electrons, but it only has 4 valence electrons. Why? Why? Because the 3d10. The 3d10 are a lot smaller. And so if you're an oxidizer, you're going to pluck off the 4p and the 4s first before attacking the 3d. And so germanium has 4 valence electrons. All these species have 4 valence electrons here. The 3d10 are considered core. And so the argon and the 3d10 would be thrown as core electrons. In other words, valence electrons are going to be the highest n. The highest n is 4. 3 is inner. Highest n is 4. This is 5 valence electrons, just like nitrogen, just like neon. So 5 valence electrons, 6 valence electrons, oxygen, sulfur, and selenium. You know, these would be the core here, etc. All right, the valence electrons are going to be most important because the valence electrons, we have something called the octet rule. The octet rule is we try to either complete the shell or get rid of it. You know, complete it with 8 or get rid of it. We'll consider it more later. And so the valence electrons can be written as Lewis symbols like this here. You know, so sodium has 1 valence electron, magnesium is 2. The rest are core, so we aren't going to show the core. Aluminum 3, silicon 4, like carbon. Phosphorus is 5, like nitrogen. Sulfur is 6, like oxygen. Chlorine's 7, like fluorine. Argon's 8. Argon has the octet. And so that's what elements are after. Octet. And sometimes it's too hard, like sodium has to gain 7. Well, sodium's not going to gain 7, so it's just rather lose 1 and then be left with a core. Same thing, it's easier to lose on the left. It's easier to gain on the right. You know, chlorine would either have to lose 7 or gain 1. Well, it's easier for it to gain 1. It can happen though, of course. You know, chlorine can lose 7, like in perchlorate, you know, lose 7. So number of valence electrons is very important, and Lewis symbols are going to be very important here as well. This is the issue with the size here. When we go from hydrogen to lithium, the size is going to increase because we're adding another shell. When we're going from lithium to sodium, another shell. So first shell to second shell. So we're adding the second shell, third shell, fourth shell, fifth shell, sixth shell. So the atoms are getting bigger because we're adding more shells of electrons. However, if we're in the same shell, the atoms get smaller as we go across. The atoms are getting smaller as we go across because we're adding more protons. And more protons are going to act like a tractor beam in the same shell. Obviously, if you add another shell, it's going to be hard for the tractor beam to work. But if you don't add another shell, we're just adding an electron in the same shell, you know, then the tractor beam can work. And so the atoms shrink in size as we go left to right. So beryllium is smaller than lithium, boron smaller than beryllium, etc. There we go. There. And so atomic radius, these are the size trends here for atomic radius. The biggest atoms are down here, cesium. Francium would be even bigger. This is radius. And so the size ranges from about, 74, 70. Actually, the smallest would have a diameter of about 62. The biggest here is about 500, but francium is even bigger. So maybe in the 600s. And so atoms range from about 100 picometers in diameter to about 600 picometers in diameter. The biggest atom would be francium here. That's too big. It should be the scale somewhat. So smallest atom, top right, biggest atom, bottom left. Those shells. All right, let me stop here for the PowerPoint, and then let's take a look at, I posted these on Piazza as well. Let's take a look at answering some of these questions on quantum. Oops. Okay, it's break time. All right, let's take a break then. Now. Okay, let's, I'm gonna pause the recording here. Let's take a 15-minute break. So 141, we'll be back. Okay. All right. How long ago did I forget? Did we miss all of that?
Yeah,
Shoot.
I think so.
All right, there's gonna be a huge gap, unfortunately. Yeah. So we do. That was from the last break then, 41. 20 minutes. So we missed 20 minutes. Let me think. What I'm going to do about it. In those 20 minutes, did I talk about? In those 20 minutes, you're going to have to generate this, energy level diagram up to here. Up to here, the fourth shell. Dang it. And then I talked about valence and core electrons. I think I talked about valence and core electrons before the break. Is that correct? Okay, good. Yeah. All right. Well, I don't remember exactly everything I covered in the last 20 minutes. Maybe, repetition. Maybe I'll cover it again. Just normally by going through it. We'll see. I'll try to do more repetition here. So, Krypton, the easiest thing to do is to generate the, if we want to figure it out, let's just go ahead and generate the entire energy level diagram for Krypton. That would probably be the best. Except I'm not going to use the, this. They have the energy level diagram drawn out for us. I don't want to use that. I want to just draw it myself. And you should be able to draw it yourself as well. And so to answer number 6 is probably best just to go ahead and draw out the entire energy level diagram. And we should get good at it, I think, the more times we draw it out. And so the lowest energy orbital here is going to be the 1s or the 100. And then that's going to be followed by the 2s or the 200. And then the 2p, like this. or the 2, 1, negative 1, 2, 1, 0, 2, 1, 1. Now krypton's going to fill the fourth shell, so we got to keep going. So this is the first shell. This would be the second shell. The third shell is going to be 300, and then, which is a 3s. And then we have the 3 Ps. 3 Ps would be 3, 1, negative 1, 3, 1, 0, and the 3, 1, 1. Now the 3Ds are going to go on the next shell. And so the next shell is going to consist of the 4s, getting tilted here, which is the 400, followed by the 3Ds. And so we have the 5 3Ds over here. And the 3Ds are going to be the 3, 2, 2, minus 2, 3, 2, minus 1, 3, 2, 0, 3, 2, 1, 3, 2, 2. So 3D. And then to complete this shell, we'll have the 4 Ps. And the 4 Ps are going to be the 4, 1, negative 1, 4, 1, 0, 4, 1, 1. Okay, so we have the 4 shells there, or the 4 rows of the periodic table. First shell is just the 1s. Second shell is the 1s and the 2s and 2p. The third shell here, yes. And the fourth shell, yes. No, actually I lost it. And so krypton's here, so we're going to fill the fourth shell right here. And so we fill the first shell, the second shell. Okay, so let's go ahead and do that. I should have drawn this more to the right. Here, if I can move it. Okay, starting here, we have hydrogen, with 1 electron, and then helium, second electron there. That fills up the first shell. We're done. The second shell starts off with lithium, 1 electron here. There's 3 electrons. Beryllium's 4 electrons. And that fills the 2s subshell. So we filled up. Now we've got to jump to the 2p subshell. 2p subshell is going to start off with boron, and then carbon. Hund's rule says 1 at a time, parallel spins. That's carbon. Carbon has a total of 4 valence electrons here. Nitrogen has a total of 5 valence electrons here. 2 core electrons. The core electrons don't participate in the chemistry. Then we go to oxygen with a total of 6 valence electrons, so we're going to have to pair that to fluorine, to neon. So once we get to neon, so we filled up the first shell with helium, and then we fill up the second shell up to neon. So this neon. Now we're going to go to work on the third shell. Here, the third shell is going to begin with sodium, one electron here, and then magnesium has 2 valence electrons. So we fill up the 3s subshell, and then we start working on the 3p subshell. Aluminum, silicon, phosphorus, sulfur, chlorine, argon. So once we fill up this third shell, we're at argon. And so this completely filled up argon. And then we'll start work on the fourth shell here. Excuse me. The fourth shell begins with potassium, like this. And then calcium, here, potassium, calcium, and then scandium, here, 3D, scandium. like this. Now, this is tricky because how many valence electrons does scandium have? Now, the interesting thing here is this is scandium. Scandium is a metal, and so metals get oxidized. The oxidizers come along and take electrons. Now, if we're looking at the 3D is like this clover leaf kind of shape here. And so here's my 3D orbital, and there's one electron in it, spin up. And so I'll put one electron in here, spin up. And the electron can be anywhere in this clover leaf, pretty much. And so this is my 3D. 3D is slightly higher in energy. Do you see? It's higher in energy. So off-bow principle says we fill the 4s first and then the 3D. But this is the odd thing. The odd thing is the 4s. Now, the 3Ds are like 9 times bigger than the 1, n equals 1. You know, n equals 3 is about 9 times bigger. But n equals 4 is like 16 times bigger. You know, so we got 9, so it's almost double the size. Not quite double the size, but kind of a lot bigger. And so when we're looking at the 4s are kind of twice as big, you know. This will be the 4s. And the 4s is going to have 2 electrons, you know, one spin up and the other spin down. And, you know, they're in the same orbital, so they'll try to keep distance from one another like that. Excuse me. Hopefully not corona or anything like that. But getting back to this. Now, if you're an oxidizer, let's say you're fluorine coming along and you want electrons. What electrons do you think would be easier to take? The 4s or the 3D? And so you're a fluorine atom is seeking electrons. You want to take electrons. You're going to take electrons from scandium. What do you think is going to be easier, to take it from the 4s or to take it from the 3D? You might think it should be the 3D because the 3D are slightly higher in energy. But it's not. You know what it takes it from? It takes, the fluorine is just going to take the outermost electrons. The outermost electrons are 4s, although the highest energy electrons are the 3D. It's weird. It's weird. And so in this case, scandium has 2 valence electrons. But now once fluorine takes these 2, let's say 2 fluorines come along, a third fluorine comes along. Once these 2 are gone, then the only electron left is the 3D, and the fluorine will take that as well. And so first it's going to take the outermost, the 4. So these 2 get plucked off first, and then this one. Normally it's the highest energy ones that get plucked off. So we call these the valence, and this is the core, but this is a reactive core. It's not like argon, you know. This doesn't get touched. Neon doesn't get touched. Helium doesn't get touched. But this would get touched because it's just a single electron all by itself in the 3D subshell. And so technically, scandium has 2 valence electrons plus 1 more that's reactive. And so it's a pseudo third valence electron. Think of it that way. But anyway, that's scandium, and then after scandium comes titanium. Let's go with white again. Titanium, vanadium, chromium. Now, weird thing happens with chromium here. Chromium we expect to be 4s2, 3d4. You know, 2 electrons in the S, 4 electrons in the D. But chromium is one of the exceptions. Chromium is weird, the electron configuration. Because if we're at chromium, which is here, this would be chromium. It should just follow in line. So we got 4s1, 4s2. So we got 4s2, 3d1, 3d2, 3d3, 3d4. So if I look at vanadium, vanadium is going to be this for electron configuration. Electron configuration for vanadium is argon, which will start here. And then we'll jump over here, 4s1, 4s2. So argon 4s2, total 3D3. And this would be correct. Chromium, what we expect for chromium is argon, 4s2, 3d4. But filled, okay, subshells. Let's look at D subshells. Filled D subshells are stable and unreactive. So D10. Filled D subshells, D10, are stable and unreactive. Okay, that's filled, completely filled. Now, half filled has some additional stability. Half filled D subshells have a little stability, have some stability. It has to do with symmetry in a way. Let's say you have a cake. And so a complete cake is good. A complete cake is D10. And so you have a whole cake, it's good. What if you had a half a cake? D5. And so you got a half a cake. Do you think that's all that great? Well, you might think, no, it's not all that great, but because of Hund's rule, it is. Because Hund's rule means you don't slice the cake vertically. And so Hund's rule says that you don't slice this vertically because of the way we fill the orbitals. When you have half a cake, you have to slice it horizontally. And so if we take a full cake and slice it horizontally, it's going to have the same symmetry as a full cake. So this is D5 here. This is not D5. We slice this horizontally so it maintains that spherical symmetry. In fact, when we have a filled P subshell, it looks like a ball of electron density, electron cloud. When we have a filled D subshell, it looks like a ball or sphere of electron cloud. When we have a half filled, it's the same thing. It's a ball or a sphere. And so it maintains that symmetry like this of the D10. Now, if we take another slice out of it, then we're going to have a chunk taken out of it. But chromium is weird because what happens is this. This is expected. And what's observed is that chromium is argon 4s1 3d5. And so what happens in chromium is one of these s orbitals gets promoted to D to half fill it because the half filled has some stability. And so for chromium, one of these s orbitals gets bumped up here to half fill this, and we end up losing the electron here. So it comes out as 4s1 3d5 to have that half filled symmetry. Once we go to manganese, then it doesn't matter. Manganese is argon. It's already half filled. 4s2, 3d5. We didn't have to promote any electron there. And so chromium is one of the exceptions. There's one more exception that you need to know. There are two exceptions here. And so chromium is not 3d4. It's going to be 3d5. Manganese is also 3d5. And then iron, cobalt, nickel, what comes up? Copper, and zinc. And so iron would be 3d6, 4s2, 3d6. Chromium's 4s1, 3d5. Cobalt is 3d7. Nickel is 3d8. But copper we expect it to be 3d9. But 3D9 is like 3D10 with one slice taken out. So if you have one slice of this cake missing, then it doesn't have that symmetry it once had. But it can regain that symmetry here. And so copper is the other exception. Copper turns out to be 4s1, so take one of these s electrons to fill up that d to 3d10. We can only promote one, so chromium is the only exception here because we can promote one to half fill it, and copper is the exception here to 3d10. So zinc is normal 3d10 like that, and so we would only lose those two electrons for zinc. And so this would be chromium. How about copper? Okay, let's take a look at copper. Copper would be kind of the same scenario here. It's clear. So for copper, you know, we got the 1s, 2s, and the 3 2p's, and then the 3s, and the 3 3p's, and then the 4s, and then the 3d's, 5 of them, and then the 4p's, 3 of them. So for copper, this is filled, second shell's filled. Third shell's filled. Now let's go to the fourth shell. Copper sits right here. And so we got 4s2, 1, 2, 4s2, 3d 1, 2, 3, 4, 5, 6, 7, 8, 9, 3d 9. 1, 2, Hund's rule, 3, 4, 5. Now pair, because it ran out. 6, 7, 8, 9. Wow, just one electron short of filling the D. Well, filling the D has some additional stability. And so what happens with copper, it's one of the exceptions, what happens with copper is we promote this S electron over here. That way we can fill this. We have to get rid of that. And so for copper, the electron configuration comes out as 1s2, 2s2, 2p6, 3s2, 3p6, that's third shell. Fourth shell is going to be 4s1, 3d10. That's it. And so these are the core. This would be the argon core, 4s1, 3d10. And so typically it's just said argon, 4s1, 3d10. Electron configuration for copper. So chromium promotes one s electron to half fill. Copper promotes one electron to completely fill. The others aren't. So if we go to zinc, zinc is just normal, you know, 4s2, 3d10 will be zinc. So we're looking at krypton to answer those questions for krypton. Let me go back to that. So got sidetracked there, but you need to know those things that I got sidetracked on. Okay, you should be able to draw the to this. All right, for krypton, we've filled up the fourth shell. So I'm just going to fill them all with electrons here. So let's fill up the first shell. That would be helium. Fill up the second shell. Be like neon. Fill up the third shell. I'll use 100 this time. Argon. Fill up the fourth shell. 1, 2, 3, 4, 5 singles, and then pair. All right, so how many electrons have ml equal -1? So ml -1, 1, 2, 3, and then there's a -1 here, 4. And so 4. How many with L equals 2? So L equals 2 is over here. So this is L equals 0. This is L equals 1. This is L equals 2. So when I look at L equals 2, I have these guys here. How many electrons? 10. 10. N equals 4. How many have N equals 4? So I got 2, 4, 6, 8. How many have M sub s minus 1/2? Half of them do. And so how many electrons do I have here? 2 plus 8 is 10, plus 8 is 18, plus 18 is 36. So half of them would be 18. Okay. And so easiest is probably just draw the whole diagram and then figure it out from there. Construct an energy level diagram for each in the ground state. Ground state's just the lowest energy. You know, a light photon can come in here and excite an electron up to a higher energy state. It's fine. Sodium, carbon, bromine, iron. All right, let's do that. So let's see where sodium is on the periodic table. Sodium, carbon, bromine, iron. Well, if we have the periodic table here, then sodium is, well, this is hydrogen. It'll be lithium, sodium, potassium. Sodium's right here. So we just got to go here. So energy level diagram, 1s, we got 2, 2s, 2, 2p, 6, 1, 2, 3, 4, 5, 6, it's here, and then 3s1. That would be it. Okay. We could also put in the quantum numbers here as well. So that would be the energy level diagram. And so here, sodium would have 1 valence electron, you know, the outermost electrons here, and the rest are core. These are core electrons here, 1 valence. Okay, did I miss a question? What's next? Carbon. Okay, let's go back. Carbon is here. That's carbon here. So we fill up the first shell and then fill up the 2s, and then we have 2 electrons and 2p. I already did carbon. The carbon would be 1s with 2, so we fill that up. Fill up the 2s, 2 electrons, and then the 2p only has 2 electrons, 1, 2. 2 electrons. And so Hund's rule says they have to be singles, parallel spin. So this would be the energy level diagram. Now, here we have core electrons, 2 core electrons, And then here's the valence. And so carbon has 4 valence electrons altogether, max. 2 in the 2s and 2 from the 2p's. Bromine. Bromine. So here we have we got fluorine, chlorine, bromine. So we fill up the first shell, the second shell, the third shell, and then we're in the fourth shell, and we almost fill it, just 1 electron short of filling the fourth shell. So let's take a look at that. Bromine, so we got 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. So we're going to fill up the first shell. We fill up the second shell. It'll be like neon. First shell would be like helium. Fill up the third shell like argon. And then the 4s is filled, the 3d is filled, and the 4p are partially filled. So the 4s is filled, the 3d is filled, and the 4p is almost filled, you know, because the 4p, we end up here. This is bromine. And so we're just 1 electron short of filling it. So 1 electron, 2 electrons, oops, 3 electrons, 4 electrons, and we got 5 electrons. We're at bromine. We just need 1 more electron to fill it. So bromine would like to take 1 more electron to fill up the fourth shell. So these are the valence electrons here. Now, how many valence electrons does bromine have? Now, this is tricky here because of 3D, but the 3D are exceptionally stable. You know, so the filled D subshell is pretty stable. And so these, even though they're in this same shell here, these are considered core. They're considered core because they're inner shell electrons. Whereas the 4, you know, 4s and the 4p are big. And the 3d are small. And so bromine has 2, 4, 6, 7 valence electrons. Bromine has 7 valence electrons. This filled D subshell is folded into the core, you know, as far as reactivity goes. And so when we see this filled D subshell, that's unreactive. So these are the valence. These are going to be much more reactive. We got 7 valence electrons here. Bromine. Iron is next. I can see where iron is. How many electrons does iron have? We could do it based on the number of electrons as well. But this is scandium, titanium, vanadium, chromium, iron, cobalt, nickel. No, I screwed it up. I'm missing one. vanadium, chromium, manganese. Oh, no wonder. Can't erase it. Oh, there it goes. Two drawing systems here. So scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. There we go. So iron's here. And so this would be, I'm going to use the abbreviation now. This is argon up to here. And so for iron, the electron configuration is easy. I would just do argon and then 4s2, 3d 1, 2, 3, 4, 5, 6, 3d6. This is not an exception where I'm going to half fill it. I guess I get to half fill it by removing one, but I can't give it to 4s. 4s is already filled. And so I could draw the, I could do the same thing for the energy level diagram. I'll start it off with argon here. Argon would include everything from 1s to 2s, to 2p, to 3s, to 3p. And so this would be equivalent to argon. And then we go 4s, which is a 400, to the 3d, to the 4p, like that. Okay, iron is going to have 4s2, 1, 2, 3d, 1, 2, 3, 4, 5, 6. So 4s2, 3d, 1, 2, 3, 4, 5, 6. The 4p's are empty, no electrons in the ground state. And so this would be it if I use the abbreviation for argon here. Okay, what comes next? Construct the atomic orbital diagram for each ground state element. Now, atomic orbital diagram, what are they talking about? Are they talking about the orbital box diagram? Let's see what they're talking about here. Yeah, they're talking about the box diagram like this. I call it the orbital box diagram. Too many diagrams. So for boron, could do that. If we look at the periodic table, for boron, we're going to have 1s that's going to be filled. And then the 2s will be filled. And then the 2p will have 1 electron. There, like that. Nickel we could get as well. So nickel will probably want to look at the periodic table. Where is nickel? Nickel would be here. And so we could fill it according to periodic table. Here I can use the Nobel gas configuration. So all of the boxes all the way up to here are going to be argon. So we'll just go argon. And then we'll start off with 4s here. We have 4s. We got 2 electrons there. 4s. And then 3d, 1, 2, 3, 4, 5, 6, 7, 8. 3d, 8. So there are 5 boxes here. 1, 2, 3, 4, 5. These are 3D. And then we have 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And so 2 more electrons to fill this here. Or can lose. You know, nickel can lose 2, maybe 3 electrons. And so that would be it. Aluminum chlorine. So it'd be similar. You could finish these. Which elements can we identify? Okay, first shell is filled, second shell is filled. Second shell is filled is neon. This one is a 4s2, 3d2, 4, 6, 7, 8. 4s2, 3d8, well, we just did that. This is nickel. This would be argon all the way up to third shell. These are energy level diagrams. These are orbital box diagrams. Here's 1 electron short in the second shell. What's 1 electron short in the second shell? Does anybody see it? What's 1 electron short in the second shell? So we're 1 electron short from filling it. So it's this element here. Fluorine. Good. That's right. Here, this is 3p2. 3p2. What is 3p2? Let's take a look. Do you see it? You can beat me to it. 3s2 would be magnesium. 3p2. Let's take a look. 3s2 is magnesium here, but 3p1, 3p2, it's got to be this element here. What is this element here? Well, this one is silicon. So silicon's right. Okay. What element is this? 4p4. 3d10, 4p4. So in the last shell, we have 4s2, 3d10, 4p4. Last shell. What element is that? Arsenic? Okay, let's verify that. So we got 4s2, 3d10, 4p1, 4p2. 4p1, 4p2. Arsenic is here. This one has got to be germanium. Germanium, yeah. 4p2. It's going to have the same. These are considered core here. We're going to have 4s2 is 2 plus 4p2. It's going to have a total of 4 valence electrons, like carbon has 4 valence electrons, silicon, germanium, 4 valence electrons. GE. Oops, not 4p2, 4p4. 4p4, sorry. I got that wrong. 4p4, what the heck is that then? Selenium, yeah. Let's take a look. This is 4p1, 4p2, 4p3, 4p4. That's correct. This would be oxygen, sulfur, selenium. This would be nitrogen, phosphorus, arsenic. So it's selenium. Selenium has 6 valence electrons. These D electrons aren't considered valence. So it's got these 4s over here and the 4p. So it's got 4s2, 4p4, 6 valence electrons like oxygen. Oxygen doesn't have these Ds, but this filled D subshell is stable, unreactive. Partially filled is not so stable and not so unreactive. So partially filled, you know, can lose electrons. It's possible. Okay, was that the last one? I think so. Yeah, that was the last one. Okay, there's some more here. You can work on these. You know. Okay, actually, I need to talk a little bit more before going through these. All right. Yeah, let me finish my PowerPoints here. And then, although it's break time. Okay, so let's take another 15-minute break and then we'll start again next. Okay, we'll get started again. Next thing we're going to look at is ionization energy. Ionization energy is removing an electron to create an ion. So for example, sodium has 1s2, 2s2, 2p6, 3s1. This is the electron configuration here. In this electron configuration, there are 10 core electrons and 1 valence electron. And so these electrons here are core. It has this 1 valence. This outermost electron, you know, has the highest n equals 3. This outermost electron is the one that an oxidizer is going to come in and strip off. So oxidizer comes in and takes this. When it takes that, then we're left with the core. Now this is stable. This is filled shell. First shell is filled, second shell is filled. And so it has stability here. If the oxidizer tries to take another electron, it's going to have a very difficult time of doing that because of this. It has to ruin that shell. That is, has to remove an electron from a filled shell, which isn't so easy to do. And so sodium is only going to go to +1. It won't go to +2 because that would involve removing core electrons. It can be done, you know, but it's going to cost you a tremendous amount of energy, so it's not really favorable to do. And so we can take the neutral atom, you know, and form an ion. Now, the ion is not the same size because here we had, the atom had 11 protons, 11 electrons, but now the ion has 11 protons, but only 10 electrons. So as it has fewer electrons and the same amount of positive charge, it becomes smaller. In fact, it becomes about half the size of it. And so let's go take a look at the size trends here on the previous slide. And so you can see the size of the neutral atom here, 190. The size of the sodium ion is 102. So it shrunk about half the size by losing that 1 electron. That turns out to be the case. Like lithium actually is more extreme, really. 60, 160, you know, a bit more extreme. But potassium is about, you know, half. Rubidium is about half. What if we lose 2 electrons? What happens to the size? So if we go to magnesium, we're going 160 to 70. Calcium, 197 to 100. Strontium, 215 to 118. Beryllium really shrinks down. Take a look, 112 to 27. So beryllium is pretty extreme. But the general rule of thumb is, if let's say we go and lose 3 electrons, so 126 to 55, so about half if we lose 3 electrons here. Cobalt, 125 to 55, about half. And so what we can say is we'll just come up with a general rule. The general rule is that cations are about half the size of the parent atom. And so the parent atom is this big, And when you form a cation, it shrinks to about half the size, more or less, you know. That's a rule of thumb. And so these species over here, you know, they have the valence electrons. It's not quite a filled shell. And so those electrons are susceptible to attack by oxidizer. And so oxidizers can come in and strip electrons off the metals and create cations here. Oxidizers have a harder time on the right end because over here, these themselves are oxidizers because they're a little bit short. So for example, fluorine doesn't want to lose any. Fluorine would rather gain. And so if fluorine gains electron, take a look at what happens to the size. We start off with fluorine neutral 60. These are in picometers. These are atomic radii in picometers. And then jumps up to 133. These are radii, so you have to double it for diameters. And so if we look at, what about 2 minus and 3 minus? When we look at 2 minus and 3 minus, and just kind of come up with some rough average, the rough average is this. Anions are about twice as big as their parent. And so we can see it here. In general, these are other kinds of rules of thumb. You know, obviously there are you know, exceptions to the rules, and so we'll just call these some observations. Some observations. You know, cations are about half the size. Anions are about 2 times the size. And so this is supposed to say cations. So cations are about half as big, the blues. Anions are about double, the greens. Yeah. Some other observations. Anions are bigger than cations. There are some exceptions, but in general, the size becomes flipped. You know, the biggest atoms are bottom left, but the biggest ions are kind of the bottom right here. So it kind of gets flipped. You can see the atoms shrink down as we go across because of that tractor beam effect, more protons, more protons. And the atoms also increase in size when we add shells. You know, when we add shell, add shell, add shell, they get bigger and bigger. But as we're in one shell and we go across, we get more protons. More protons is a stronger, like sci-fi type tractor beam, which pulls in the electron cloud, which means the atoms shrink as we go down. But take a look at what happens when we create ions. You know, when we create ions, you know, it kind of flips. Now the big ions are on the right and the small ions are on the left. Other parts though hold, you know, like sodium's bigger, potassium's bigger, rubidium's bigger. Okay. But we kind of had that weird pattern. So we have something called the ionization energy. You know, to take an electron off sodium costs you energy. Even though you might think it's stable, it's going to cost energy. How much energy does it cost? Well, if we look at sodium here, it's going to cost about 500 kilojoules per mole. That's very low. That's actually very, very low, 500 kilojoules per mole. Compared to helium. If you want to take an electron off helium, that's closer to 2,500 kilojoules per mole. So helium is very difficult to ionize. Sodium is very easy to ionize, to take an electron off. Excuse me. The ionization energy goes by size. The smallest atoms are the hardest. The biggest atoms are the easiest. And so it follows the size trends. There are a couple of blips here. You know, beryllium to boron. Beryllium, we're ionizing a 2s electron. Boron, we're ionizing a 2p. So it's slightly easier to ionize a 2p than a 2s. And then nitrogen to oxygen is another blip here. Nitrogen, you're ionizing an unpaired electron. Oxygen, you're ionizing a paired electron. It's easier to ionize a paired electron than an unpaired electron because nitrogen has 3 electrons in the p, whereas oxygen has 4 electrons in the p, so it's paired. This paired one's going to be easier to pluck off. But as the orbitals grow bigger, it becomes less dramatic, you know. Like, for example, here, this would be the 2, this would be the 3p, this would be the 4p. 4p orbitals is not really as big of a factor because pairing, you know, even when the electrons are paired in an orbital, they're far enough apart that they don't really bother one another. And so there's some minor blips. These minor blips you don't have to memorize. You know, in Chem 1A you will, but in Chem 4, don't worry about these minor blips, but they can be explained based on, you know, the orbitals. The point here is, as we go from lithium to neon, it gets smaller. As the atoms get smaller, they become harder to ionize. As we go from hydrogen to helium, they get smaller. Now, on sodium to argon, they get smaller, harder to ionize. Potassium to krypton, they get smaller, harder to ionize. Now, when we jump, you know, we jump from lithium to sodium, it should get easier. Sodium to potassium, it should get easier, although lithium and sodium look very comparable. So we can understand some chemical properties here. You know, the alkali metals, these all have 1 valence electron. That valence electron gets easier and easier to take the bigger it becomes. Like cesium's big, so it's easy to strip. Lithium's harder. Sodium becomes easier, potassium, you know, etc. Actually, this is francium here. Cesium would be here. And then potassium, whatever. Here, rubidium, that's right, cesium, francium. And so, actually, I could have just drawn it here. So francium should be the easiest to take the electron. The easiest would be the lowest ionization energy. So francium should, but francium's radioactive, so we throw in cesium there. Okay, these ones are going to be a little harder to take the electrons from because they're a little smaller. So for example, beryllium's a little smaller than lithium, so it's harder to take the electron, even though it has 2 versus 1. Still harder to take the electron. And so these guys here on the left, where they want to lose electrons, or they're susceptible to losing electrons because an oxidizer can come in and take the electrons. These are big atoms. Remember, the big atoms on the left. The big ions are on the right, but the big atoms are on the left, so we're taking electrons. These are small atoms here, fluorine, chlorine, etc. Fluorine's the smallest. It really wants an electron. Iodine's a bit bigger. So, you know, fluorine's a very powerful oxidizer. You got to watch out for this stuff. This gas is nasty. Bromine's a liquid, but it's a very volatile liquid. Volatile means it vaporizes easily. So you can see the brown vapor here, orange, red vapor. That's bromine gas. This is bromine liquid here. Iodine's actually solid. Here they're growing iodine crystals via sublimation. Sublimation means they vaporize some solid here and deposit it on a cool surface here. It's probably ice-filled or ice water-filled test tube in an Erlenmeyer flask there. So, but anyway, all these want 1 electron, you know, because they're 1 electron short of filling the shell. And once you fill the shell, then you have that additional stability from the filled shell. All these, they're too many electrons away from filling the shell, so it's better to lose an electron and go back to the core. Once they're back to the core, then it's stable. At least their electrons are stable. Keep them reacting. So the sodium, lithium metal is very corrosive, so that's why it's all discolored here. Sodium is a very soft metal. It's easy to cut. You can cut it with a butter knife. It's that soft. You know, it's easy to bend too. You know, all these have very low ionization energy, so they can be oxidized by water. You know, water is not a very powerful oxidizer, but it's strong enough of an oxidizer to oxidize the alkali metals. So lithium, sodium, potassium, all these react with water quite violently. We saw sodium reacting with water in Lake Lenore when they were doing the disposal of sodium, but we could see some other alkali metals react with. There are lots of videos of this on YouTube. Let me see if I can pull one up quickly. But the alkali metals are very reactive because of their low ionization energy. They're big atoms. Big atoms are easy to ionize. Oxidizer, even a weak oxidizer like water. Water is an exceptionally weak oxidizer, but it's strong enough to oxidize alkali metals. All alkali metals are water reactive. And so let's pick a short one. This is interesting.
If you'd like to stay strong and independent as you age, then listen to the story of my...
Here I'm working with some lithium metal, very difficult to cut. I've got a piece of sodium here, pretty easy to cut. You notice when I cut through that the fresh sodium is very shiny compared to the rest. Zoom in real quick and see if we can really get in there. So this side will reflect a lot of light. The other sides are pretty dull. And you'll see that especially with the potassium here. I'm going to go ahead and give this kind of a half cut. So for the potassium, this is the side that's freshly cut, and you can see the dullness to the other sides compared to that one. So I'm going to go ahead and take those three, and I'm going to add them to water, and we can look at the kind of reactivity of those three alkali metals with water. So here I'm going to take the lithium, and that's the water. It's going to generate hydrogen gas and lithium hydroxide. So you're going to see a pink color develop here, and then you're going to see some smoke come off, and that's either lithium metal or that's lithium hydroxide coming off there. Maybe a little bit of liquid water. But it's not as reactive as, say, sodium. So I'm going to put sodium into the next one.
a lot of the smoke is generated because a lot of these alkali metals are stored under mineral oil. If you look at the paper towel he had, the paper towel was soaked with mineral oil. Do you see all that oil? That smoke is caused from the burning oil. Lithium hydroxide is not going to cause. Lithium hydroxide should end up in the water. Hydrogen's colorless. And so that white smoke is the oil. He didn't clean it off well enough. If he cleaned it off in alcohol, it'd probably be better. And then he put in an indicator here to change color. When lithium hydroxide comes into contact with the indicator or hydroxide, it changes it to pink. It's like litmus paper. It just tells you if there's hydroxide present. In the presence of hydroxide, the indicator turns pink.
And that's either lithium metal or that's lithium hydroxide.
Lithium metal is not going to vaporize like that, nor is lithium hydroxide. I didn't review this video beforehand.
But it's not as reactive as, say, sodium. So I'm going to put sodium into the next one.
Sodium is a bigger atom, so it should be more reactive, easier to ionize. So water can attack it easier.
Sodium is actually probably going to ignite. So you'll see some orange flame, perhaps, or some sparks, or some shrapnel.
It's hard to ignite because it's smothered in smoke right now. If he cleaned it off better, it would have ignited a lot easier.
And then the last one, I'm going to go ahead and put my 2 pieces of potassium in. So this is less potassium than the other two. In terms of amount, you'll find that the reactivity is a little bit greater.
Potassium's the biggest of the atoms there, and so it's much easier, much easier to ionize than lithium or sodium. So it's going to be the most reactive of the three, it being the largest, most easiest to ionize of the three. although, you know, it doesn't look dramatically different here in terms of ionization. If we zoomed in there, it's a bit easier to ionize than sodium. Here, potassium has a lower ionization energy. A bit easier. Lithium and sodium look on par, but sodium is going to be easier. This is bigger. There are other factors that influence lithium as well. Okay, so those are the alkali metals here. And they can easily be oxidized by something like water. And water is not a very good oxidizer. Water, water, water. These are powerful oxidizing agents. Chlorine, bromine, iodine. All these species want electrons. And so here they're, let's see, they're reacting, looks like they're taking chlorine with white phosphorus. So chlorine with white phosphorus is, in other words, chlorine's going to strip the electrons off phosphorus. In this case, make phosphorus trichloride. And so let's see if we have that video. We can watch two of them, chlorine with white phosphorus and bromine with white phosphorus. Let's take a look at those. Working from home, my internet isn't so great at home. So this video is really choppy. That's not yours, that's mine. So it seemed, I'm gonna just stop it here. Oh, there it goes. Look how violent that is. You know, chlorine's a powerful oxidizer. Phosphorus is a pretty decent reducer. You know, however, if they did chlorine with sodium, it would be pretty nasty. Let's look at sodium with chlorine next, because sodium is an even more powerful reducer than phosphorus. Although that was pretty good. That's a pretty violent reaction. A redox reaction. It just dies off at the end. All right. That was good. Let's see what else they have here. This is University of Wisconsin. It's pretty good. University of Wisconsin. Search in video. Well, probably take too long to search. This is from Berkeley. I've watched this video.
In this demonstration, I am going to attempt to make sodium chloride. A very cool reaction, one of my favorites, as I always like to say. But in order to make sodium chloride from its elements, I'm going to start with elemental sodium, which I have here, a very soft reactive metal that is stored in kerosenes, because the kerosene being nonpolar is hydrophobic, prevents the water from reacting with it, as we've seen in other demonstrations, or mine. And I'm going to generate the chlorine gas, the chlorine atoms, okay, from potassium permanganate with hydrochloric acid. So the potassium permanganate, being a strong oxidizer, okay, is going to make the chlorine atoms become into chlorine atoms, chlorine ions. And from the hydrochloric acid, I'm going to add the potassium permanganate, is going to become the chlorine gas here. And you know the chlorine gas is present when you see a yellowish green. There's a little bit here that I made previously, but I'm going to pump it up, or pump up the volume, so to speak, with some acid or hydrochloric acid. Took the chloride ions, reacting with the permanganate ions, and the chloride ions, being Cl negative, are going to lose the electron, okay, be forced to oxidize by the presence of the oxidizing agent, the potassium permanganate, the permanganate ion, to make your chlorine gas. So let's make some chlorine gas. So I'm going to put some hydrochloric acid into this Erlenmeyer and then stopper it. And as I should mention, I'm in a fume hood because I am producing, okay, chlorine gas. I'm trying to fill this flask.
All right,
up.
this is some students caught that. I've shown this video before, but this bottle is labeled zinc nitrate. He's saying that's hydrochloric acid in there. So that's one of these lab rules you're not supposed to do, mislabel bottles like this, because it could potentially be very dangerous. And so this should have been labeled hydrochloric acid. It is hydrochloric acid. This is a very common reaction. Potassium permanganate, powerful oxidizer with hydrogen ions from hydrochloric acid, and chloride. And so the potassium permanganate with the H plus attacks the chloride to generate chlorine. And so we could generate chlorine on the lab scale. In the previous reaction, he just used a bottle of chlorine that you can buy. But in this one, he's generating his own chlorine using redox.
Up with chlorine gas. I'm not quite seeing the volume of gas. I'm not seeing that color change drastically. So I'm going to have to put some more acid here. I may need some more potassium permanganate. The flash should get yellowy green. Okay, and let me just add, just to make sure, because I want to make sure I'm filling that flask up. I see it getting yellowy green, but I'm just going to add a little bit more potassium permanganate into the mixture, chloride ion mixture. And of course, you can see that green color, that yellowish green color. So you can see that flask is definitely filling up with a greenish yellow color of chlorine gas. So I believe we're ready to rock and roll here. Okay, at least I can see with my colorblind eyes. You agree? You see some chlorine gas in there? Okay, we're in a fume hood. So now all I'm going to do is I'm going to take out my generating tube, and I'm going to drop some small amount of sodium into the flask. Now, it may react right away. Chances are that it won't, so I'm probably going to have to put a little bit of water on it. Okay, so I'm going to take out my generating tube. I can see my yellowy flask, and I'm going to take my piece of sodium, and I'm going to drop it, hopefully, right in the middle. Okay, reposition my camera a little bit. Okay, now, let's see if we get a nice little close-up here. What's going on? And refocus. And what we're going to do is I'm going to drop some water on this sodium metal to activate it. And we we should see a pretty brilliant reaction once I activate it. So I'm just trying to drop some water with a pipette to start the reaction. And there it is. And that white smoke you see is sodium chloride solid, the colloid. And so that white smoke is the presence of sodium chloride that we made.
Yeah. So those are tiny
And as
crystals
it
of sodium
dissipates,
chloride.
we'll see where the sodium was, where the sodium metal was, is now going to should be a crystal lattice of sodium chloride. Notice the color of the flame was indicative of how sodium metal or sodium electrons get excited and, of course, emit energy. So as this calms down, okay, we notice this is pretty thick smoke because this is essentially sodium chloride. So I can actually pour this out because it's really solid. But what I want to do is I want to wait to see what it looks like after it's done. When it's done, when all that sodium chloride dust settled was.
Let's fast forward. This time lapse.
Once the dust has settled, so to speak, kind of milky white spot. That white spot, and I'll get a close-up in a second, represents where the sodium was in highest concentration, and that is where you see some solid sodium chloride crystals. So and you will see right there, as I focus, that is where the sodium chloride is in the place of where the sodium metal was. So the sodium chloride, sodium plus ions, gave their electrons in a redox reaction to the chlorine ions, the chlorine, I should say, atoms, and became chlorine ions, and they attracted each other to form this precipitate or salt. And that was that cloudy white.
Okay, actually, this is not the one from Berkeley. There's another one that's from Berkeley where he'll take the sodium chloride he made and sprinkle it on some hot dog or French fries or something, I forgot, and actually eat it. But I'm sure he made sure it's, you don't want, there's probably some chlorine residue there, maybe some sodium unreacted. You got to be very careful if you're going to do that. But I think it was just for demonstration purposes. All right, let's take a look at that. So that was phosphorus and bromine. You know, here's another violent reaction. You know, bromine's the oxidizer, phosphorus is a reducer, like phosphorus. And then we have zinc and iodine here reacting. Zinc is a metal. Zinc is a pretty good reducing agent. It loses electron, so it's easy to ionize. It loses electrons easily. Iodine's an okay oxidizer. Well, let's take a look if that one's online so we can see what that looks like. So it's going to be iodine and zinc. And zinc.
Want to win one of the rarest BMWs in the world, plus $20,000 cash and
sometimes people grind things up in a mortar and pestle like that. Different reasons. One is to mix solids. Another is to finely divide the solid so it reacts faster. Sometimes the reactions are quite slow, especially with solids. So having a powdered one reacts faster than having a granular one. Looks like the zinc is already powdered. You can buy powdered metals. Powdered metals are a little bit dangerous though, for fire and for explosions. And so you have to watch out for powdered metals. Well, it doesn't look like there's any reaction happening. It's two solids, you know, as two solids react, you got to get them to collide with one another. Well, they don't collide, they just sit there. They may not react unless you grind them together. You notice he didn't grind, or she didn't grind them together in the mortar and pestle. A drop of water can dissolve things and get things starting to react, or react with things, just initiate the reaction. So this is forming zinc iodide. This has got to be done in the fume hood as well. The purple vapor is sublimed iodine. Is that it? I guess that was it. Oh, you didn't see much of a reaction there at all.
If you'd like to stay.
All right, so we divide up the periodic table into the metals. You know, the metals share certain characteristic properties. Properties of metals, they tend to lose electrons to form cations, yes? They have 1, 2, or 3 or more valence electrons. So +1, +2, +3 are common charges for metals that we see. It could go higher, but those have to be stabilized, like in perchlorate, they're stabilized with oxygen. They have low ionization energies. You know, these species over on the left have lower ionization energies compared to the species on the right. They form compounds with nonmetals, but not with other metals. With other metals, they form alloys or mixtures, you know, homogeneous mixtures, not compounds. With nonmetals, you know, oxidizers, they're going to form compounds. They have high electrical conductivity. Metals conduct electricity well. Also, they conduct heat pretty well too, high thermal conductivity. They're malleable. They can be hammered into sheets or different shapes, and they can be drawn into wires. You know, some more easily than others. The nonmetals, they don't have as many common features as metals, but here are some tend to gain. So nonmetals tend to be oxidizers. They typically have 4. So the 4 is kind of the tipping point, because once you're above 4, it's better to gain. You know, 4, like carbon, you can either gain or lose. You know, boron, you want to lose. Beryllium, you want to lose. Lithium, you want to lose. And so, high ionization energies, yeah, these ones don't like to lose electrons. They like to take electrons. Like chlorine's pretty unhappy if it starts losing electrons. From compounds with metals, they form. This is not supposed to be from, so that's a typo in the book. They form compounds. So metals and nonmetals form ionic compounds. Nonmetals have poor electrical conductivity except for carbon in graphite form, which has excellent conductivity. They have poor thermal conductivity. They're usually good insulators. They're brittle and non-ductile. Also, you know, they're solids, liquids, and gases here as well. Okay, so that's the periodic table here. Now let's go back. Okay, it's break time. Is it break time, or was that the last one? 2:44. I guess that was the last one. So not yet. All right. So let's go back to our supplement worksheet, and then let's take a look at that. So why don't you guys, I posted this on Piazza, so why don't you guys work through some of these problems here, go through. We have 2 more. We got the practice questions on the periodic table, and then we have practice exercise on the periodic table. Not all of these are, you know, some of these are just kind of trivia type questions, not really practical. But let's see, why don't you go through some of these? Actually, let's see. I don't like a lot of these questions, actually. So let's take a look at the questions I like. This one's good. Twelve, 13. So let's take a look at doing these. Three, 4, 5, 6, 9, 12, and 13. Yeah, that's good. All right, so let's do some breakout rooms, and why don't you try working on these? Let's see, we got 18. We'll create this manually. Yeah, we'll do that.
Can you put on the screen number 12 and 13 so I could take a quick picture?
Yeah, I'm gonna scroll it. Okay.
Thank you.
Yeah, no problem. Just give me a minute to set up the rooms. What happened? Okay, so I have these rooms. Why don't you just work on these problems here? And then I'm going to give you another set to work on. Just a moment. You'll need a periodic table to do these. I'll be back. Okay, let me know if you need any help or if you're finished with the first series of questions. Oh, sorry, Vanessa, I accidentally moved you. Oh, what just happened? Maybe I moved you, maybe not. Yeah, Carlos, I'm going to post the link on Canvas. Are you guys working together or alone for the most part? Are you all finished with the part one? Okay. Yeah, I'm going to post a link on Canvas. So just upload it on Canvas, those questions. And then what we're going to do is we're going to complete this. This is a little puzzle. So the first puzzle piece is X, that should be the element with the lowest ionization energy. And so fill in the rest of the pieces. The next puzzle piece is Y. Where does Y, which box does Y go in? Okay. And so you'll upload these on Canvas. The second part here is also on canvas. So figure out which box Y goes in, and then you have Q, and then RT, etc. You'd also let me know if you have group preferences. I can make sure to try to group you with others. I guess I forgot to record it. Shoot again. Okay, did you guys, where are you guys at now? All right, we're going to get started again. So we're going to jump into the next chapters, 12 and 13. 12 and 13 deal with structure. And so this is an interesting video, but it's a little old, but it's still relevant. And some of the graphics aren't as good as modern day graphics, but let's check it out. This is molecular structure and health. Actually, let me change the speakers. Okay, so hopefully the audio works on this.
This is a production of the Chemical Education Material Study. The number and variety of living systems is remarkable. More than 1 billion species currently exist. We now know that a principal factor in this large number is the billions of ways that 4 rather simple chemicals can vary their sequence in forming DNA genes. We are also discovering that many illnesses can be identified at the molecular level. This provides information for the design and synthesis of molecules, which can be used to treat the disease. If we examine living cells under the microscope, like these plant cells, or these bacteria, or this animal tissue, we can see the movement, growth, and cell reproduction, which are the result of successions of chemical reactions. In attempting to control these reactions, physicians have used various substances, some from nature, and some synthesized in the laboratory. Many of the compounds found to be useful were discovered by trial and error. One such compound was sulfanilamide. Let's demonstrate the effect of sulfanilamide on bacterial growth. A nutrient medium in a petri dish is used to sustain growth of bacterial organisms. These bacteria, harmful to humans, are carefully transferred from a stock preparation. They are gathered in a wire loop and streaked onto the nutrient medium in both compartments of this dish. A small piece of sterilized filter paper is wet with a sulfanilamide solution and placed here in time-lapse photography. The bacteria multiply and become visible in the area around the paper disc. The clear zone shows that bacterial growth has been stopped. This inhibition is due to the sulfanilamide from the disc. How does sulfanilamide stop the growth of these harmful bacteria? First, let's examine the function of one of the key molecules that exists in the bacterial cells. It is called para-aminobenzoic acid. Using a geometric symbol retaining the general contours of the molecule, we'll follow its action within the cell. In the cell with the acid is an essential bacterial enzyme. In order for the enzyme to perform its active role, it must first combine with the para-aminobenzoic acid. Only then can the enzyme catalyze the further reactions necessary to cell life. When we examine the structure of the acid molecule and compare it to a molecule of the drug sulfanilamide, we find that they are much alike. This large portion of each is identical. The electron charge distribution in each molecule is also similar, and their general configuration are the same. Using geometrical representations again, let's include sulfanilamide in the bacterial cell along with the normally present acid molecule. The sulfanilamide too can react with the enzyme. But the sulfanilamide not only fails to activate the enzyme as a catalyst, also prevents the acid from doing so. Thus, metabolism stops and the bacterial cell dies. The effect of sulfanilamide on cell growth was found by trial and error. But the discovery that sulfanilamide is structurally similar to an essential molecule accounted for the action of the drug. This principle of structural similarity helps us to predict which drugs might be effective against specific diseases. Consider, for example, the use of drugs in the treatment of cancer. By means of tissue culture technique, human cells are kept alive for microscopic observation. Here are normal human skin cells under the microscope. In time-lapse photography, cellular activity appears accelerated. We know of very few differences between the chemistry of normal cells and these cancer cells. One remarkable difference, however, is that the cancer cells grow faster. And another difference is that during the faster growth, the cancer cells use abnormally large amounts of a substance known as uracil. Can a structural modification of the uracil molecule be used to disrupt fast growth of the cancer tissue? Let's follow some of the steps a biochemist takes in answering such a question. He is familiar with the visible parts of a single cell, like this one undergoing division. We see a set of dark ribbons in the middle of the cell. These dark objects are chromosomes, and they are intimately connected with the process of cell growth. The biochemist has learned to collect chromosomal material from cells and has found that it is composed of deoxyribonucleic acid, or DNA. Because DNA is a large, complex molecule, it is helpful to break it into its component parts and identify them. These component parts can be separated from each other by the technique of paper chromatography. After treatment with an acid, a small drop of the chromosomal material is placed on this large piece of filter paper. The paper is rolled into a convenient shape for the next procedure. We have selected a solution in which the chromosomal material is readily soluble. This is placed in the bottom of a glass cylinder. The solvent is drawn up the filter paper by capillary action. After 12 hours, the solvent front has risen this far. The filter paper is removed and allowed to dry. It is then rolled in the opposite direction, back in a different solvent. This will ensure a further and better separation of the molecular components. These components are not visible under ordinary light, but if we place an ultraviolet light under the dried paper, we can see that the solvent has distributed the components of the chromosomal material. This distribution has occurred because the solvent front competes with adhesion to the paper for the chromosomal materials, so the components move according to their molecular size and solubility. Thus, different compounds derived from the chromosomes are separated. We'll cut out one of these marked areas and dissolve the material from the paper with another solvent. Now we can analyze the dissolved material with an infrared spectrometer. A characteristic spectrum is produced by each component separated in the chromatography procedure. The absorption spectrum produced by one of these extracts is compared with the known absorption spectrum of the chemical thymine. Apparently, chromosomes contain thymine. Similar analysis of the other components shows that each has its own characteristic spectrum. Identification shows that besides thymine, chromosomes contain adenine, guanine, and cytosine. How do our uracil molecules, which are present in such large amounts in cancer cells, relate to the constituents we have extracted from the chromosomes? We know that these constituents, along with other building blocks, are necessary to make DNA molecules, which in turn have a part in forming the chromosomes. Biochemists have shown that uracil is the substance from which thymine is formed. Without uracil, thymine will not form, preventing the synthesis of DNA, which in turn prevents the formation of the chromosome. When we examine the molecular structures of uracil and thymine, we find that there is but one position in which these structures differ. To convert uracil into thymine, a hydrogen atom here must be replaced by a methyl group such as this. Let's symbolize uracil with its hydrogen atom, like this, to follow its action within a cell. First, a chemical group called a sugar phosphate residue becomes attached to the uracil molecule. The modified uracil compound then forms a complex with an enzyme. Somehow the enzyme converts the hydrogen into a methyl group to form the thymine compound. This molecule is then freed for eventual synthesis into the DNA chain. How can we disrupt this mechanism and stop cell growth? Clearly, one point of attack is the original uracil molecule. This molecule can be altered in many ways. One of the most promising has been to replace this hydrogen with a fluorine to give 5-fluorouracil. 5-fluorouracil has a number of advantages. First, the hydrogen and fluorine are almost the same size, so that both molecules should fit into the enzyme. Second, the chemistry of a carbon-fluorine bond differs from that of a carbon-hydrogen bond, so that the enzyme might find it difficult to replace the fluorine with a methyl group. And finally, the changed polarity may allow the fluorine compound to adhere more firmly to the enzyme than would a uracil compound. Thus, we predict that the 5-fluorouracil, just like the uracil, will attach itself to a sugar phosphate residue and then fit into the same place on the enzyme the uracil would have used. But once in place, The strong bond to fluorine will prevent the enzyme from replacing the fluorine with a methyl group. And finally, we predict that the strong polarity of the 5-fluorouracil will cause such strong adherence to the enzyme that the normal uracil compound will be prevented from reacting, and that, with the enzyme blocked, the essential chromosomal material cannot be made, and the cell will die. Let's test this prediction in the laboratory. Here are two cultures of cancer cells. Those on the left have been treated with 5-fluorouracil. Compare the action of these cells to that of the untreated cells on the right. The untreated cells continue to show rapid growth. The 5-fluorouracil treatment is seen to stop cell division, produce cellular enlargement, and eventually contraction and death. But are we sure that the cancer growth is stopped in the manner we predicted? Instead of the 5-fluorouracil blocking the enzyme as we have suggested, and using this means to kill the cell, is it possible that the 5-fluorouracil is incorporated into the DNA, inhibiting its function? To determine where the 5-fluorouracil is acting in the enzyme DNA, let's conduct an experiment on some human cancer cells grown in the laboratory. A sterile pipette is used to transfer the cells into a large flask, which contains a nutrient medium. This permits continued growth so that we will have enough cells for our experiment. The cells are kept in suspension by a magnetic stirrer and incubated for several days. Here is specially prepared 5-fluorouracil containing radioactive carbon-14. By tagging the 5-fluorouracil with these radioactive atoms, we can determine where the 5-fluorouracil goes in a human cell. We'll add a small amount of the radioactive 5-fluorouracil to the living culture. In about half an hour, these radioactive molecules will be incorporated into the cancer cells. The cancer cell suspension is poured into large cups to be spun in a centrifuge. The spinning collects the suspended cancer cells into a pellet on the bottom of the cup. The liquid is discarded. By this means, the cells from large volumes of the culture medium are finally concentrated into one cup. The cells are then resuspended in cold sodium chloride solution to dissolve the DNA. The low temperature retards enzyme action. This cell suspension is placed in a blender. The violent action of the blender fragments the cells to facilitate dissolving DNA. After storage overnight in a refrigerator, the DNA dissolves, and then the solution will be spun very rapidly in a centrifuge. This spinning action separates the residual cell proteins which contain the enzymes. A high-speed centrifuge is required because the large size of the DNA has made the solution viscous. After the centrifuging, the liquid fraction contains the soluble DNA. The pellet contains the undissolved residue. According to our theory, if the 5-fluorouracil is incorporated into the DNA molecule, radioactivity should be detected in the liquid. Otherwise, it should be found in the pellet. The next step is to concentrate the DNA. The liquid is drawn off and injected into alcohol, which precipitates the DNA. These threads of DNA material can be readily collected on a glass stirring rod. A sample of the DNA fraction is removed for measurement of its radioactive content. The protein pellet is retrieved from the centrifuge tube. The meter shows that there is no radioactivity in the chromosomal material. However, the protein fraction does show radioactivity. The experiment proves that the radioactive 5-fluorouracil is not incorporated into the DNA. Though the chemistry is oversimplified as portrayed here, it does show that the structural similarity of 5-fluorouracil to uracil is of crucial importance in its ultimate effect, the enzymatic synthesis of genetic material. Uracil is currently one of the most effective chemotherapeutic agents for treating skin cancer. For example, chemotherapy with methotrexate can lead to complete remission for 97% of children treated for acute lymphocytic leukemia. But we need even more effective and less toxic chemicals, especially for lung cancers and brain tumors. In the past, most medicines have been discovered by trial and error, even by accident. Aspirin, the most widely used medicine in the world, was used for almost 100 years with no idea as to how it reacted in the body. Modern techniques are allowing us, now some mechanisms are understood. We are beginning to be able to design molecules the living system needs for recovery.
I don't know what happened. Okay, so let me resume the video.
kept alive for microscopic observation. Here are normal human skin cells under the microscope. In time-lapse photography, cellular activity appears accelerated. We know of very few differences between the chemistry of normal cells and these cancer cells. One remarkable difference, however, is that the cancer cells grow faster. And another difference is that during the faster growth, the cancer cell
Can't see the video. You couldn't see the video from the beginning or just from now? Okay, let's try this again.
One remarkable difference, how it accelerated.
All right, can you see the video now? Is
We
it
know of very
working?
few differences between the chemistry of normal cells
Okay.
and these cancer cells. One remarkable difference, however, is that the cancer cells grow faster. And another difference is that during the faster growth, the cancer cells use abnormally large amounts of a substance known as uracil. Can a structural modification of the uracil molecule be used to disrupt the fast growth of the cancer tissue? Let's follow some of the steps a biochemist takes in answering such a question. He is familiar with the visible parts of a single cell, like this one undergoing division. We see a set of dark ribbons in the middle of the cell. These dark objects are chromosomes.
Okay, I think
They
I
are
backed up a
intimately
little
connected
too
with the
far.
process of cell growth.
Did you guys see the part where he hydrolyzes and then separates? Yeah.
This is placed in after 12 hours.
This is called paper chromatography, and it's used to separate molecules based on their solubility, slight differences in their solubility. Here. And then one particular molecule was found here, and then another here. And just slight differences in the solubility will carry one molecule further than the other on the paper. And then he was able to cut these out and then analyze them using, I think, infrared spectroscopy to identify what the molecules were in each of those fractions.
According to their molecular size and solubility. Thus, different compounds derived from the chromosome. Now we can analyze the dissolved material with an infrared spectrometer.
This is an old one. Modern day infrared spectrometers will take that spectrum in a second.
Characteristic spectrum is produced by each component separated in the chromatography procedure.
But the spectrum looks the same. Sometimes there's better signal.
The absorption spectrum produced by one of these extracts is compared with the known absorption spectrum of the chemical thymine. Apparently, chromosomes contain thymine. Similar analysis of the other components shows that each has its own characteristic spectrum. Identification shows that besides thymine, chromosomes contain adenine, guanine, and cytosine. How do our uracil molecules, which are present in such large amounts in cancer cells, relate to the constituents we have extracted from the chromosomes? We know that these constituents, along with other building blocks, are necessary to make DNA molecules, which in turn have a part in forming the chromosomes. Biochemists have shown that uracil is the substance from which thymine is formed. Without uracil, thymine will not form, preventing the synthesis of DNA, which in turn prevents the formation of the chromosome. When we examine the molecular structures of uracil and thymine, we find that there is but one position in which these structures differ. To convert uracil into thymine, a hydrogen atom here must be replaced by a methyl group such as this. Let's symbolize uracil with its hydrogen atom like this to follow its action within a cell. First, a chemical group called a sugar phosphate residue becomes attached to the uracil molecule. The modified uracil compound then forms a complex with an enzyme. Somehow the enzyme converts the hydrogen into a methyl group to form the thymine compound. This molecule is then freed for eventual synthesis into the DNA chain. How can we disrupt this mechanism and stop cell growth? Clearly, one point of attack is the original uracil molecule. This molecule can be altered in many ways. One of the most promising has been to replace this hydrogen with a fluorine to give 5-fluorouracil. 5-fluorouracil has a number of advantages. First, the hydrogen and fluorine are almost the same size, so that both molecules should fit into the enzyme. Second, the chemistry of a carbon-fluorine bond differs from that of a carbon-hydrogen bond, so that the enzyme might find it difficult to replace the fluorine with a methyl group. And finally, the changed polarity may allow the fluorine compound to adhere more firmly to the enzyme than would a uracil compound. Thus, we predict that the 5-fluorouracil, just like the uracil, attach itself to a sugar phosphate residue and then fit into the same place on the enzyme the uracil would have used. But once in place, the strong bond to fluorine will prevent the enzyme from replacing the fluorine with a methyl group. And finally, we predict that the strong polarity of the 5-fluorouracil will cause such strong adherence to the enzyme that the normal uracil compound will be prevented from reacting, and that, with the enzyme blocked, the essential chromosomal material cannot be made, and the cell will die. Let's test this prediction in the laboratory. Here are two cultures of cancer cells. Those on the left have been treated with 5-fluorouracil. Compare the action of these cells to that of the untreated cells on the right. The untreated cells continue to show rapid growth. The 5-fluorouracil treatment is seen to stop cell division, produce cellular enlargement, and eventually contraction and death. But are we sure that the cancer growth is stopped in the manner we predicted? Instead of the 5-fluorouracil blocking the enzyme as we have suggested, and using this means to kill the cell, is it possible that the 5-fluorouracil is incorporated into the DNA, inhibiting its function? To determine where the 5-fluorouracil is acting, in the enzyme or the DNA, let's conduct an experiment on some human cancer cells grown in the laboratory. A sterile pipette is used to transfer the cells into a large flask, which contains a nutrient medium. This permits continued growth so that we will have enough cells for our experiment. The cells are kept in suspension by a magnetic stirrer and incubated for several days. Here is specially prepared 5-fluorouracil containing radioactive carbon-14. By tagging the 5-fluorouracil with these radioactive atoms, we can determine where the 5-fluorouracil goes in a human cell. We will add a small amount of the radioactive 5-fluorouracil to the living culture. In about half an hour, these radioactive molecules will be incorporated into the cancer cells. The cancer cell suspension is poured into large cups to be spun in a centrifuge. The spinning collects the suspended cancer cells into a pellet on the bottom of the cup. The liquid is discarded. By this means, the cells from large volumes of the culture medium are finally concentrated into one cup. The cells are then resuspended in cold sodium chloride solution to dissolve the DNA. The low temperature retards enzyme action. This cell suspension is placed in a blender. The violent action of the blender fragments the cells to facilitate dissolving DNA. After storage overnight in a refrigerator, the DNA dissolves, and then the solution will be spun very rapidly in a centrifuge. This spinning action separates the residual cell proteins which contain the enzymes. A high-speed centrifuge is required because the large size of the DNA has made the solution viscous. After the centrifuging, the liquid fraction contains the soluble DNA. The pellet contains the undissolved residue. According to our theory, if the 5-fluorouracil is incorporated into the DNA molecule, radioactivity should be detected in the liquid. Otherwise, it should be found in the pellet. The next step is to concentrate the DNA. The liquid is drawn off and injected into alcohol, which precipitates the DNA. These threads of DNA material can be readily collected on a glass stirring rod. A sample of the DNA fraction is removed for measurement of its radioactive content. The protein pellet is retrieved from the centrifuge tube. The meter shows that there is no radioactivity in the chromosomal material. However, the protein fraction does show radioactivity. The experiment proves that the radioactive 5-fluorouracil is not incorporated into the DNA. Though the chemistry is oversimplified as portrayed here, it does show that the structural similarity of 5-fluorouracil to uracil is of crucial importance in its ultimate effect, the enzymatic synthesis of genetic material. 5-fluorouracil is currently one of the most effective chemotherapeutic agents for treating certain types of skin cancer and colon cancer. About 40 anti-cancer agents are in clinical use today. For example, chemotherapy with methotrexate can lead to complete remission for 97% of children treated for acute lymphocytic leukemia. But we need even more effective and less toxic chemicals, especially for lung cancers and brain tumors. In the past, most medicines have been discovered by trial and error, even by accident. Aspirin, the most widely used medicine in the world, was used for almost 100 years with no idea as to how it reacted in the body. Modern techniques are allowing us to learn about living systems at the molecular level and what changes cause loss of health. Now some mechanisms are understood. We are beginning to be able to design molecules the living system needs for recovery.
Okay, stop here. I didn't prepare a PowerPoint for this. We're just going to go through. I'm going to combine chapters 12 and 13, just call it structure. Okay, what we're going to focus on are something called Lewis structures. Lewis. Oops. And for Lewis structures, we'll need the Lewis symbols. And so we can review some of the Lewis symbols here. For example, group 1, like hydrogen, lithium, sodium, all these have one dot. One dot refers just to one valence electron. And then group 2, like beryllium. And beryllium is going to have 2 dots or X's, sodium, magnesium has 2 valence electrons like that. And then we go to group 13 or group 3, which is going to have 3 dots. The way we draw the dots, there's a usual convention, but it's not always adhered to. This is a single, this is a pair, this is 3 lone ones. That'd be aluminum. And then next to, what else would be? Boron would be the same. Oops, I'm offset a little bit here. Boron. Carbon, 4 dots in 4 regions. Usually we have 4 different regions of space around the atom here. So carbon has 4 valence electrons. Same thing with silicon, 4 valence electrons. In fact, all of these in the same family would have the same number of valence electrons. Like that. And then next to carbon's nitrogen. Nitrogen will have, the screen is blank. Oh, geez. Why is that happening? Do you see anything on the screen now? Yeah, okay. Can you drawing on it? So nitrogen has 5 valence electrons. Yeah? Okay, good. The way we draw, this is the typical convention. You know, when we have 1 valence electron, we just draw 1 dot. When we have 2, we usually draw a pair, like beryllium, magnesium, etc. With 3 valence electrons, like boron, we draw 3 singles, like this. When we have 4 valence electrons, we draw 4 singles, like this. You know, regardless, you know, for example, 4 valence electrons would consist of 2s2, you know, 2p2. And so that gives us a total. 2 of these electrons are the s, 2 are from the p. But we don't differentiate, you know, we just group these together because these have the same n equals 2 here. That would be the highest n. Now the core electrons are the 1s2. So these are the core, or the inner shell electrons. And these would be the outer shell electrons, or outer electrons. And so these are the electrons that are going to react. And so again, we don't differentiate, it just has 4. You know, nitrogen has 2s and 3p. So altogether 5 valence electrons, and we'll just group them together. Here we pair one up and then have 3 singles, like this, over here. Phosphorus would be the same, a pair and then 3 singles. Arsenic's the same, the family. And so if it's a member of this family, we draw the Lewis symbol all the same, you know, for the members of the family. When we go to fluorine, oh, actually I missed oxygen. When we go to oxygen, all right. I'm having some glitches here. It doesn't seem to work. So my eraser's not working here. So we go to oxygen. Oxygen has 6. And so normally what we'll do is we'll pair up 4 like this, 2 pairs, and then have 2 singles here and here. It's oxygen. Sulfur is the exact same. Now where we draw the pair doesn't matter. You know, it just has 2 pairs. So I could draw a pair up here, a pair down here, and then a single on the right and a single on the left. Doesn't really matter. But there are 4 regions of space. 2 of them are occupied by pairs. 2 of them are occupied by singles. We go to fluorine. We're going to have 3 pairs, this, and then 1 single. Chlorine's the same way, you know, 3 pairs and 1 single. I didn't draw them the same here. And then finally, neon. Neon is going to have 4 pairs. 4 pairs gives us 8 electrons. And so neon, this is special. This has what we call the octet of electrons. The octet is a filled shell. We've completely filled the shell. This is neon, Ne. I forgot the E. Below neon, we have argon. Argon is also going to have a filled valence shell, or an octet. Here, an octet. Argon is going to be neon, because it has another shell of electrons, but this outermost shell is filled. The inner shell on argon would be the 1s2, the 2s2, the 2p6. That would be the inner shell. And the outer shell would be the 3s2, 3p6, which gives us 8 electrons in the valence. And then over here would be the core. And so neon and argon have the same valence shell, what we call electron configuration. The electron configuration would be an ns2 np6, where we can just change n. So for neon, n would be 2. For argon, n is 3. For krypton, n would be 4. And so the outer, and the core again don't react. So even though argon has a bigger core, it's going to be unreactive. We're not going to see it. And so these species over here want, want to take an electron. And so these species over here want to lose electrons. And if they lose electrons, then they're going to be left with a core electron shell configuration. Transition metals become a bit more tricky. For the transition metals, we look at those individually because how we do Lewis symbols, we don't normally do Lewis symbols for these. Maybe scandium we could, but these we don't normally do Lewis symbols for. Transition metals are a little bit more complicated because of the d electrons, the partially filled d electrons. Now, the partially filled d electrons, you count those as valence, or do you count those as core electrons? So it becomes, sometimes they're reactive, sometimes they're unreactive in that sense. So it's better to look at these and treat these in more depth than these other ones here. And so we could do some simple reactions here for example, oxygen and magnesium. So a simple reaction would be magnesium, which is a reducing agent, and oxygen. Now this is going to be atomic oxygen. Normally we have diatomic oxygen, but what we're going to do is we're going to break apart the diatomic oxygen, so we have atomic oxygen here. And then oxygen is going to see these electrons. Well, oxygen wants those electrons to complete its octet. And so, oh, is it break time? All right. Let's go. All right, let's go. We'll take a break then. Since we're getting close to the end, how much break do you want? Do you want the regular standard 15-minute break, or can you get by with a shorter break, like a 10-minute break? Since there's no response, we'll go with a 15-minute break. So I'm going to stop, and then we'll come back after the break. Okay, we're back here. Just going to resume what we were talking about earlier, but here we have oxygen. And oxygen is going to try to strip the 2 electrons here. It's going to use energy to take these electrons. So oxygen comes over here and tries to pluck off the first one. Then it gets closer to having an octet. Then it's going to come over here and try to take the second one. Now, to take the first one, it's going to cost some energy, but to take the second one, it's going to cost about double that amount of energy. And so it definitely costs some energy to do this, to form the magnesium 2+ ion. Now, what's the reason for that? The reason for that is to maximize bonding. This is why compounds form. Compounds form because bonds are stable in general, and the more bonds we can have, or the stronger bonds that we can have, the bigger the driving force for these types of reactions are. Also, we can go back to our other driving force for redox as well, but in this particular case, we're going to form an ionic compound. And so this is the Lewis symbol or structure. These are Lewis symbols down here. This is going to be a Lewis structure here that I'm going to draw next. And the Lewis structure for this is going to be like this. Magnesium is going to have no more valence electrons. It's only going to have core electrons. Now, when a Lewis symbol or Lewis structure has a charge, we draw square brackets around it and then indicate the total charge. This would be the total charge here on the outside. So this would be the magnesium ion. And over here, now oxygen is going to have an octet. Now the bond here is going to be quite stable because there's a 2 plus and a 2 minus. So there's going to be a strong electrical attraction. If it could go 3 plus, that would be even better. 3 plus and a 3 minus would form a stronger ionic bond. But the problem with going to a 3 plus, a 3 minus is, the next electron, the next oxygen would try to take from magnesium would more electron. Electrons cost like 10 times more energy to take than a valence electron. And so it's cost prohibitive in that sense. And then in the other sense, where would oxygen put that extra electron? Because it's already filled the shell. And so in order to accommodate one more electron to go to 3 minus, oxygen would have to put the electron in the next higher energy shell, which would be destabilizing. And so normally why we target these octet numbers and the core is because that's where we can get the maximum charge or strong bonds without going too extreme, too extreme being having to go core or having to go next shell. Or also we'll see we can form the maximum number of bonds, because the more bonds we can form, the more stable it is. And so this is an example of an ionic compound. Ionic compounds are held together by ionic bonds. The ionic bond is not shown here. The ionic bond we take as an attraction between positive and negative ions. And so this would be the ionic bond. Here, ionic bond. There. And so that's the gap. And then normally what we're going to form is a lattice type structure. In a lattice type structure, we're going to have magnesium ions. Magnesium ions are small. Oxide ions would be bigger. And so we have magnesium oxides arranged in a 3-dimensional lattice that's packed together like this. And so this would be an ionic lattice showing the packing together of the ions, the cations, which are the smaller, and the anions, which are the bigger species here. So ionic compound. Let's move on here. Now, oxygen is going to want an octet. Magnesium's willing to sacrifice, but there are things that aren't willing to sacrifice. So let's take an oxygen versus an oxygen. If we have oxygen versus oxygen, then something happens here. Both oxygens are going to try to take 2 electrons from the other oxygen. Well, I'll answer that question later, but basically when we do ions, when you do, let's say, this, what would you name O2? Is that oxygen? Or is that peroxide? Well, we can easily tell which one it is. Oxygen doesn't have a charge. Peroxide has a charge. Otherwise, you can't tell, And so species, a formula is always going to have. I'll never tell you, never, ever to not write it, because this is like Dr. Jekyll and Mr. Hyde. Na versus Na plus. These two are totally different in terms of properties. totally different properties just because of this. In fact, what's most important in chemistry is electrical. You know, when we're thinking about chemistry, electrical interactions are the most important, and therefore charges are critical in chemistry. Nuclear chemists, I mentioned this a long time ago, nuclear chemists don't know about the charge because they're working with different types of forces than regular chemists. But regular chemists, they're concerned. For nuclear chemists, you know, I talked about very reactive, like redox reactions. Even the most reactive redox reactions aren't very energetic compared to nuclear reactions. And so like a dynamite explosion versus a nuclear explosion are in two different leagues. You know, nuclear explosion is much, much more energetic than the most violent chemical explosions. And so nuclear chemists aren't so interested in charge, but chemists are. You know, that's the most important thing. So we'll talk about that some more later, but I would never tell you to not write the charge. If you don't write the charge, then maybe I told you that nuclear chemists don't write the charge, but because nuclear chemists, you know, when they do an alpha particle, it's just He24. They don't write the 2+ here. But for a chemist, an He2+ is horrendously, I don't know if anybody remembers it, but what was so dangerous about alpha radiation? Alpha radiation was dangerous because of its radioactivity. It turns out, no, alpha radiation is not radioactive. What's dangerous about alpha radiation is its charge. That 2+ charge in an extremely small volume makes it terribly reactive. So, well, we'll see some more. And so both of these oxygens are going to try to take 2 electrons. This oxygen is going to try to pull that electron off. This oxygen will try to pull that electron off. And they're going to get in a tug of war. This oxygen will try to get this electron here. This oxygen will try to get this electron here. And so they end up in a tug of war. Who will win? Will it be the left oxygen that wins or the right oxygen that wins? Who will win? When magnesium and oxygen get in a tug of war, oxygen wins, magnesium loses. But when oxygen gets in a tug of war with oxygen, neither wins. It becomes a tie. And we end up with a situation like this. This is where they're going to have to share the electrons to get the octet. And then if they're sharing the electrons, we have to count it funny as well. So when we count it, this oxygen has 8 electrons or an octet around it. And this oxygen has 8 electrons or an octet. And we have to double count these. These are the bonding electrons here that are being shared. So we end up with something like that. This is called a covalent bond, where we have sharing versus one takes it. And then we have one more type of bond here. This one is specifically a non-polar covalent bond. We can also have a polar covalent bond. So if hydrogen gets in a tug of war with oxygen, hydrogen's a bit weaker. And so oxygen's going to have more pull. So oxygen's going to want 2 electrons, so we'll put in 2 hydrogens there. And so what happens in this particular scenario is that the same thing. Oxygen is going to try to pull this, and then hydrogen is going to try to get a duet. You know, to fill the first shell only takes 2 electrons. Oxygen will pull this one, and hydrogen will try to pull this one. Oxygen has a stronger pull. And so what we end up with is a situation where it's not ionic. In an ionic bond, we're going to form full-on ions, where one atom loses, the other atom gains. In this particular scenario, what we form is something called a polar covalent bond, where oxygen is going to have a greater pull on the pair of electrons here. Just draw it like that, to the detriment of hydrogen. Like that. And so this would be a polar covalent bond. Not quite ionic. And so it all depends on the tug of war. So let me just summarize this really quick over here. And that is, okay, this is not working. The three types of bonds that we're going to have ionic, in which there's a winner take all. And so that would be something like sodium and chlorine. Chlorine pretty much takes the electron from sodium. And then we have a tie. We'll have an intermediate one all right in the middle here. We have a tie, which is chlorine versus chlorine. Chlorine versus chlorine, both of them want one more electron to complete the octet. And so there's nonpolar sharing. So this would be covalent. And then we have an intermediate. An intermediate would be something not as weak as sodium and something not as strong as chlorine. So for example, hydrogen and chlorine. And so I'll draw it like this, although maybe I'll draw it. Let's see. Yeah, something's wrong with my computer. Can't erase this. So we'll get the electron cloud here. The electron in these two pairs, excuse me, this pair, these two electrons belong entirely to chlorine. Here, for the most part, the electron cloud is around chlorine, but hydrogen hasn't completely given up. And so hydrogen's hanging on to a little bit of the electron cloud here, but it's been polarized towards chlorine. Here, it's pretty much non-polarized. That is, the electron cloud is being shared evenly between the two chlorines here. And so we have it. And so the charge that results here, when chlorine gains that extra electron, it gets a negative charge, and then sodium's left with a positive charge here. So sodium ends up with a positive charge here. Here, chlorine doesn't end up with a full electron. It just ends up with most of the cloud. And so what we say is that chlorine gets a partial negative charge, and hydrogen gets a partial positive charge, where this symbol is delta, delta minus, delta plus, representing something less than -1. This would be anywhere from 0 to -1. This would be anywhere from 0 to +1. And so maybe it's like -0.8. And this is +0.8. Here, this would be 0 and 0. There's no charge on either. And so 0 and 0. This would be nonpolar. And so again, it's going to range from ionic to covalent. And then this would be polar covalent in the middle here. And so the most polar bond we can have is an ionic bond. And so this is increasing polarity here and decreasing polarity there. Okay. Well, I'll leave that the puzzle. You can maybe I'll schedule some more time if you guys want for that to complete it, but you bring that in as well. Just try to figure out the puzzle with the periodic table there, and submit that along with the other questions for the quiz. But I'm going to wrap things up here today. I think we'll be back to normal tomorrow. But were there any questions before I sign off? The puzzle is supplement. Let me show it to you. Here. Okay, this is the puzzle here. And we just fill in this. X is the element with the lowest ionization energy. So the element with the lowest ionization energy should be the biggest. The biggest on this chart is going to be at the bottom left. So we'll put an X here. Y is the most reactive nonmetal. So the nonmetals are on the right. Which one's most reactive? Well, these group 18 are the noble gases. The noble gases aren't reactive. The most reactive would be the smallest of the nonmetals that don't have an octet. And so that would be fluorine. That would be here. So Y goes here. And then we go on. Q only has one proton in its nucleus. Well, the only species with one proton would be hydrogen. And so this must be Q here. Does that make sense? Yeah, the questions are the ones below. So I did the first three here, and then you can fill in the rest. It shouldn't take very long to do this. If you need more time, yeah, you can do it. Try to finish it today and turn it in tomorrow, but if you need more time, it's all right. There's no firm due date on this. So just get it in. You can. All right, well, are there any other questions before we wrap things up? It depends. If you did it by yourself, you can turn it in by yourself. You don't have to turn it, or if you did it with a group, you can turn it in, just one per group. That's fine too. No, the test is not going to include chapter 12 and 13. Chapters 12 and 13 will be on the next one. So just through chapters 11 for this test. Okay. I got behind, but I'll catch up because some of the other chapters aren't so long. Chapter 11 for Chem 1A, you know, it goes into quite a bit of depth there. So that's why I spent a little extra time on quantum. And then this is really important. 12 and 13 is important. You have to get good at doing Lewis structures. Okay. And question 31, which on the test, or question 31 on from the other? Question 31. Okay, you want to take a look? We can take a look at question 31. Let's take a look at that. Well, I'm going to stick around and answer the question for number 31, but that's it. Okay, so if you want to leave, go ahead. If you want to stick around, if you have some questions on this test, that's fine too. Let's take a look. No, I'm sorry, I never said not to put charges. When did I ever have to put charges on formulas? That would be something I would never, ever, ever say. I'm sorry if you misunderstood, but I would never say, because a formula is going to depend on charge. So for example, here, if we go to something like nitrite, you know, if you go to nitrite, nitrite is NO2 minus, but NO2 is not called nitrite. NO2 is called nitrogen dioxide. And so I'm not sure where you heard not to put the charge. You know, that is very, for me, that is very unusual. Unusual to say not to put the charge on. You know, I don't know. Every formula I did in class, I wrote the charge. And so otherwise, you know, this is why when we were going through the periodic table, I was asking what's the charge, like borate, you know, BO3 minus. And so I'm not sure why there was that. Yeah. So, but I wouldn't, you know, I wouldn't worry about it too much at this point because although you would have lost some points there. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe 10 points there, 11 points. It depends on how many you didn't have the charges there. There are other places where you could make it up. Yeah, where did you guys hear that? Can you find that on the recording or the video, and then show me where I said that not to write the charge for ions. There's going to be some extra credit at the end, you know, on the final exam, but also the quizzes should help. So there are other places where you can opportunities where you can make up the points. There's still a lot of points left, so I wouldn't really worry about it right now. If it does become an issue, then we could talk about it some more later. But you know, I'm just kind of curious where you guys heard that. Oh, I was surprised. I was surprised because I saw a number of people didn't write the charges there. So I kind of wonder where that happened. So can you point out to me, and then I got to be more careful too. Otherwise, you know, ions are always going to have a charge, and it's very important because, again, it's very important to know the charge. It makes a huge difference. Like even in solubility rules, like +1 -1 versus a +2 -2. +2 -2 is going to be a lot less soluble in general. Not to worry about it so much. What the charge? No, the ions. What I said about nomenclature is you have to have it memorized. You know, for nomenclature, you're really going to hurt yourself if you don't memorize. And I notice a lot of people kind of just look these up, you know, but you really have to have it down by the time we get to the final. You know, that is, you have to have the formulas and the charges memorized, both. The quiz grades are going to be, I'll get through those, you know. I don't have a date for all of them, but I only made it partway through. The last one I was inputting, was the blood alcohol, but I didn't get everybody's blood alcohol quiz grade in there. And so that's the last one, and then I got to do the rest. So blood alcohols should be pretty soon. And then we'll have some more as we go along. Yeah, you guys, it's not just the formulas, it's also I mean, when I say the formulas automatically include the charge, like chloride, you know, chloride is Cl minus. This is atomic chlorine, totally different name, atomic chlorine, you know, this is molecular chlorine. Yeah, this is nitrogen, atomic nitrogen. You know, nitride is N3 minus, and so this is a totally different name. You know, this is sulfur trioxide, which is a gas. This would be sulfite, which is an ion. These have totally different oxidation states too. +6, +4. So I'm not sure where you got it. I always do the charge. Every single ion, I never would ever write an ion without a charge. Otherwise, it's just not an ion. It's just, to me, it's just bizarre to not have a charge. And so, yeah. And I know if you don't write the charge in there, yeah, you're going to lose a lot of points because these were all or nothing. And so we'll have, you know what we'll do? I'll have another exam, just nomenclature, you know, on Canvas, probably. We'll have an exam, nomenclature exam. And then you can make up some points. I'll throw in some extras in there and make up some points that way. Do you have, yeah, except the nomenclature exam is going to be different. It's not going to be like a take home. It'll just be like a Canvas style thing. I'll do a little trial before we do one, but that'll be near the end. So make sure by the end of this term, you have them memorized, and then you'll do fine there. The formula and the charges. Okay. Yeah, the quizzes that could be, but I think I inputted more than 2 quizzes. The grades on more than 2 quizzes. Let's see. So if you only have 2, then that means you're missing a grade. I'll have to take a look. So I'm on quiz 4, so you should have at least 3 grades in there with blood alcohol. Well, the quizzes, if I'm on quiz 4, quiz 1 was the student information sheet. Upload. Quiz 2, okay, this was quiz 1, the student information sheet upload. It's quiz 1. Quiz 2 was measurements. Measurements, that was in-class participation. So I just looked at, I was asking, okay, this is part of the quiz. What is the measurement? And so we were doing some measurements in class. It's quiz 2. Quiz 3 was the swimming pool, that was upload. This was group. This was measurements was individual. Swimming pool was group. Blood alcohols group. Nomenclature's group. But nomenclature, I gave a chance because there were some mistakes on the nomenclature. And so I sent it back saying, correct them. If you correct the mistakes, then you can get 100% on it. Otherwise, I'm just going to grade it as is. So if I don't receive a correction on the nomenclature, I'll just grade it as is. I already went through these here, the nomenclatures. I already went through blood alcohol. Everybody that turned in the blood alcohol will get full credit for that because everybody got it right. The nomenclature, one group had everything right, but there were some errors on some of the nomenclatures on some of the other groups. So there's a chance to correct those and get full 4 points for that. The single replacement, I haven't gotten to that one yet. These I haven't gotten there yet. And so far we've had 11 quizzes, including today's. Why didn't it show up? I thought, oh, here, this is it. I need to rename this. This is going to be quiz 11. Let me rename it. All right, so this is quiz 11, the periodic table questions plus completing the puzzle. That's what we're doing today. For lab 1. That, there was no, are you talking about the measurements here? Okay, this one we didn't have. There's no upload. There was no, this was the homework problems. We went through all the homework problems. And I just ask everybody, this is the quiz, so submit your measurement, you know. And so it's just based on the chat window. So if you submitted the, did you submit a measurement on the chat window? If you submitted a measurement on the chat window, there were, altogether there was something like 6, and I took 4 of them, 4 out of the 6. So if you answered 4 out of the 6 measurement, then you got full credit on this one. This is not the, this is not related to the lab. This is related to the chapter homework. The lab is, yeah, we need to submit the lab too. And so we had the safety contract. The lab is, where is the lab? I guess I didn't put the lab up here. I need to put the lab here, but you know, we aren't done with the lab. We are done with the Bunsen burner lab. And so let me put that up here. But we aren't done with the measurement lab. So let's do the lab. You know, the type of Bunsen burner we used was a Tyrrell burner. Oh, I forgot how to spell Tyrrell. 2 L's. Maybe not 2 L's, maybe 1 R. Maybe it just isn't in there. Just call it the burner lab. And so this one you could upload. I didn't put it up here, but let me do it right now. That's right. I forgot how much are the labs worth?
Professor, when are the labs due?
Labs are due usually a week after we finish it. And so the Bunsen burner lab should be due Thursday.
Okay, thank you.
Except that's when we finish it. We didn't finish the measurement lab though. And so the measurement lab will be due next week. And so just the Bunsen burner lab, but the Bunsen burner lab is pretty much done, I think. Labs are worth, I guess they're only worth 10 points. I thought they were worth more. Well, not that much. The quizzes are worth 4. The quizzes are, 2 quizzes are almost a lab. The quizzes are a lot of points. This burner lab was pretty short, so it should be an easy 10 points. You still have to do, I don't know, I think most people finish the true false questions on that. Maybe. Alrighty. All right, so lab, burner lab. The next lab is going to be the measurements lab. Yeah, go ahead and upload it here. Maybe other people did it with a safety contract. Just didn't have it. Yeah, some of the stuff, Piazza, the lab is from the lab manual, from the bookstore. The form is. But other things are here. The safety rules are here. So I posted those last week. Safety rules. This should be an easy 4 points here. Just read this, print your name, sign it, write your student ID and date it. That's it. So it should be easy 4 points. Safety quiz. But yeah, that's there. But it's also, I took this from your lab manual. So this is what's you'll find in your lab manual. Here. Okay. Yeah, no problem. Thanks. Okay, were there any other questions? The lab manual is not on Piazza. Lab manual you have to get from the bookstore, El Camino. Or you might be able to get like the forms, like if you just watch the videos, you don't need the lab manual. If you watch the videos, then you can just complete it, you know, based on, I took some shots of the lab manual, so you just have to write in, you know, so you could just do that way, or you can just buy it from the bookstore. I can't distribute it because of copyright issues. But to get a paper copy anyway is cheaper than photocopying it or printing it out on your printer, probably. Okay, well, if there are no other questions, then yeah, thanks. We'll see you guys tomorrow. Tomorrow I'll be back in the place. There's a lot better internet at the office I go to. And so the internet at my house isn't so great. So, all right, I'll see you guys tomorrow. Yeah, thanks for bearing with all the technical problems today. Okay, talk to you later.